October 1st, 2025. Midnight. The United States government shuts down. NASA's website goes dark. Social media falls silent. And precisely then, at that exact moment, an interstellar visitor named 3I-ATLAS enters the observation window at Mars 30 million kilometers away, where our orbiters wait with cameras pointed at the sky. Coincidence? Maybe. But here's what kept me awake as all this unfolded. The timing is so perfect it almost feels scripted. Was this bureaucratic chaos, or the most convenient blackout in modern space history? Stay with me through this late-night investigation, because by the end, you'll know exactly what happened during those silent days in October, what the data actually shows, and why this story matters more than we think. Part 1. The shutdown and the arrival, the unnerving coincidence. First, let me explain what we're dealing with here. On October 1st, 2025, the United States government officially shut down. Not with a bang, not with ceremony, just the quiet click of funding running dry. Federal agencies go dark, websites stop updating. NASA, the agency that put boots on the moon and rovers on Mars, posts a single message on its homepage. NASA is currently closed due to a lapse in government funding. For the average person scrolling the news, this is Tuesday in Washington. Budget theatre, political gridlock, nothing new. But here's the thing that should make you sit up in your chair. At almost the exact moment that NASA's public face goes silent, we enter the optimal observing window for the third confirmed interstellar visitor ever detected in human history. An object designated 3I-ATLAS, also catalogued as C/2025N1, begins its closest approach to Mars. The timing is so precise it feels scripted. Let me explain what we're dealing with here. 3I-ATLAS isn't from our neighbourhood. It's not a rock that's been circling the Sun since the solar system's formation. This object came from somewhere else, from the space between stars, travelling on what astronomers call a hyperbolic trajectory. That's the mathematical way of saying it's not gravitationally bound to our Sun. It's passing through, a cosmic traveller that will visit us once and never return. We've only confirmed 2 others like it before. The first was Oumuamua in 2017, that cigar-shaped enigma that sparked 1,000 debates about whether we'd just witnessed our first brush with alien technology. The second was Borisov in 2019, which looked more like a normal comet and calmed some nerves. 3I-ATLAS is number 3, discovered on July 1st, 2025 by the ATLAS survey system, which is fitting since that's literally what it's named after. Now, the European Space Agency had scheduled something special. They'd planned an observing campaign for October 1st through 7th using their Mars-orbiting spacecraft, Mars Express and ExoMars Trace Gas Orbiter. The geometry was perfect. On October 3rd, the comet would pass within roughly 30 million kilometres of Mars. That might sound like a lot, and it is by everyday standards, but in astronomical terms it's practically a handshake. Mars would be closer to this interstellar visitor than Earth would be for months. The Martian orbiters, equipped with cameras and spectrometers, would have a front-row seat to something humanity had never observed before, an interstellar object at relatively close range from a planetary vantage point other than Earth. But here's where the story gets interesting in that uncomfortable, prickling the back of your neck kind of way. During a government shutdown, NASA suspends most of its public-facing operations. The websites don't get updated. NASA TV goes quiet. Press releases stop. Social media accounts fall silent. The agency's communication machinery, which normally churns out stunning images and mission updates daily, simply stops. Only what they call accepted operations continue, the activities necessary to protect life and property. That means the International Space Station keeps flying. Critical satellites keep operating. But the public doesn't get to see what's happening. It's not malicious. It's policy, codified in appropriations law. But the effect is the same. The lights go out just as something extraordinary happens in our cosmic backyard. So why did audiences hear less than they expected during this window? Part of it is straightforward. NASA's shutdown meant fewer eyes watching the data streams, fewer hands writing press releases, fewer people authorized to update the public. But there's another factor. From Earth, 3I-ATLAS was difficult to observe during this period. Its position in the sky meant low elongation, meaning it appeared close to the Sun from our perspective. Try looking at something faint when it's nearly in line with a blinding spotlight. Ground-based telescopes struggled. The Martian orbiters were genuinely our best shot at getting good data during those critical days. Our only eyes, in a sense. And those eyes belong to agencies operating under very different circumstances. ESA continued as normal. NASA went quiet. Now, it's worth noting that Hubble had already imaged the comet back in July, providing constraints on the nucleus size but not nailing down a precise measurement. That's important for what comes later, because without knowing exactly how big and bright the nucleus is, we can't pin down its mass. And without mass, we're guessing about composition. Is it ice and rock like a normal comet? Is it something denser? The uncertainty leaves room for speculation, and speculation, as you'll see, is exactly what filled the vacuum during that quiet October week. Let me give you the timeline clearly so you can see the synchronicity. July 1st, 2025, discovery. The comet is spotted, its path calculated, and astronomers realise what they have. October 1st through 7th, Mars window, the optimal days for close observation from Martian orbit. October the 29th through 30th, perihelion, the comet's closest approach to the Sun. Late November through December, reappearance to Earth-based observers after solar conjunction. During the Mars window, when the interstellar visitor is at its most accessible to our robotic explorers, NASA's public voice is silenced by bureaucratic circumstance. Online, rumours started almost immediately. Claims of missing images, telemetry gaps, frames that were posted and then pulled, redacted data files, unscheduled spacecraft manoeuvres. Most of it was noise, the kind of speculation that flourishes in information vacuums, but some of it was harder to dismiss. Were there actual gaps in the data, or just gaps in communication? That's the question I'm going to help you answer. We're going to separate what we can verify from what we merely suspect. We're going to look at the paper trail, the spacecraft logs, the orbital mechanics. We're going to test whether the silence was coincidence or something else. Because here's the thing, if you wanted to observe something in space without the public watching, a government shutdown provides the perfect cover. Not because of conspiracy, but because of policy. The mechanisms already exist to keep things quiet during a lapse in appropriations. The question isn't whether those mechanisms were used. They were. That's the law. The question is what was happening while those mechanisms were in place, and whether what happened matches what we're being told. So was this an unnerving coincidence, or was it a perfectly timed curtain falling over something we weren't meant to see clearly? Let's find out who was actually watching from Mars, and why it felt so disturbingly quiet during the days that mattered most. Part 2, the planetary observers and their silence. Let's talk about who was actually at Mars when 3I-ATLAS made its closest approach, because if you're going to understand why the silence felt so strange, you need to know who had the capability to observe and what they said they were doing. The roster of spacecraft orbiting Mars during October 2025 reads like a fleet. On the European side, you have Mars Express, which has been circling the red planet since 2003, carrying its high-resolution stereo camera. Then there's the ExoMars Trace Gas Orbiter, a more recent arrival with its colour and stereo surface imaging system and its Nomad spectrometer suite. On the American side, NASA operates the Mars Reconnaissance Orbiter with its phenomenal high-rise camera, arguably the most powerful telescope ever sent to another planet. There's MAVEN, the Mars Atmosphere and Volatile Evolution mission, designed to study the Martian upper atmosphere but equipped with instruments sensitive to solar wind and plasma. And on the surface, you have Perseverance and Curiosity, the rovers, which aren't designed to look at comets, but could theoretically capture wide-angle sky frames or photometric data if commanded to do so. The European Space Agency was transparent about their plans. They publicly announced an observing campaign for October 1st through 7th, timed to coincide with the comet's closest approach of roughly 30 million kilometres on October 3rd. Their stated goals were to capture shape hints from the coma, measure activity levels, and possibly obtain spectra that could tell us about the comet's composition. This wasn't secret. ESA mission scientists gave interviews to Space.com. They talked about the geometry, the challenges of observing a faint object at that distance, and their excitement about studying an interstellar visitor. This is normal mission operations, the kind of public engagement you expect from a space agency doing science. NASA's position during the shutdown was different, but not sinister. The agency's continuity plan, which is public record, states clearly that space satellite operations continue during a lapse in appropriations when necessary to protect property and life. That's the legal language. What it means in practice is that the Mars orbiters keep flying. Flight controllers keep monitoring spacecraft health. If an orbiter needs a thruster burn to avoid debris or adjust its trajectory, that happens. But public communications pause. The websites stop updating. The press office sends everyone home. So the operational picture is this. NASA's Mars assets could operate during the shutdown. They likely did operate, at least at a minimal level. What didn't happen was public reporting about what they were doing. Now let's distinguish between confirmed plans and speculation. ESA's observing campaign is confirmed. They said they were doing it, they explained their goals, and their statements can be found in archived interviews and press releases. What about NASA's spacecraft? There were no official NASA announcements about MRO or HiRISE targeting the comet during the Mars window. That doesn't mean they didn't try. It means we don't have confirmation. In the weeks leading up to October, some planetary scientists, including Avi Loeb, publicly expressed expectations that HiRISE would be tasked to observe 3I-ATLAS. Loeb is the Harvard astronomer who's been the most vocal proponent of the idea that Oumuamua might have been artificial, so his interest in this object is understandable. He has a track record of pushing for aggressive observation campaigns of interstellar visitors. But expecting something and confirming it are different things. Let's talk about capabilities because that matters for understanding what was even possible. HiRISE, which stands for High Resolution Imaging Science Experiment, is an incredibly powerful camera by spacecraft standards. It can resolve features as small as 30 centimeters across when imaging the Martian surface from orbit. But 3I-ATLAS wasn't on the Martian surface. It was 30 million kilometers away. At that range, HiRISE's resolution would drop to roughly 30 kilometers per pixel, maybe better under ideal circumstances. You're not going to resolve the nucleus. You're not going to see surface features. What you could get is photometry, basically measuring how bright the object is and how that brightness changes over time. You could potentially detect asymmetries in the coma, the cloud of gas and dust surrounding the nucleus. You could gather data on the comet's shape through its light curve. That's not nothing. That's scientifically useful, but it's not the kind of close-up imagery people imagine when they hear HiRISE pointed at a comet. From Earth during this period, observing 3I-ATLAS was genuinely difficult. Low elongation meant the comet appeared close to the Sun in our sky. Observatories have to be very careful when pointing instruments near the Sun because of the risk of damage and the overwhelming glare. Some observations were possible, particularly from high-altitude sites during twilight, but they were challenging. This made the Mars-based assets even more strategically important. They had a geometry advantage. They were looking at the comet from a different angle, one that didn't involve fighting the Sun's glare. If we were going to get good data during early October, Mars was the place to be. So let's address the silence directly. During a shutdown, NASA's website updates slow to a crawl or stop entirely. NASA TV goes off the air except for ISS coverage, and even that's minimal. Social media accounts post nothing. The press office doesn't issue releases. This is all policy-driven. The Anti-Deficiency Act, which is the federal law that governs government operations during funding lapses, prohibits agencies from spending money they don't have. That includes paying web developers to update sites, paying communication specialists to write press releases, even paying for some server costs in extreme cases. The result is informational silence. But here's the critical distinction. Informational silence is not the same as operational silence. The spacecraft keep flying. The data keeps coming down, at least the critical safety data. What doesn't happen is the curation and public release of science data. As of October 1st, there have been no NASA press releases detailing Mars Reconnaissance Orbiter or rover observation products of 3I-ATLAS. Is that suspicious? Not necessarily. It's expected during a shutdown. Science results take time to process and release even under normal circumstances. During a shutdown, that pipeline stops completely. The data might be sitting on a server somewhere, waiting for scientists to return to their desks, waiting for funding to resume so people can be paid to analyze it. Or the observations might not have happened at all. Or they might have happened and produced nothing interesting. Without official confirmation, we're left guessing. What we can say with confidence is this. ESA openly stated they were attempting to observe the comet during the Mars window. NASA's assets were capable of observing, and safety-level operations continued during the shutdown. But public communications from NASA were paused by policy. This creates a divergence in the narrative. From Europe, we heard about plans and intentions. From America, we heard nothing. Not because NASA scientists weren't interested, but because the machinery of public communication was turned off. That silence, combined with the extraordinary nature of the event, an interstellar visitor at Mars during a rare government shutdown, created the perfect conditions for speculation to flourish. And flourish it did, in ways that we're about to explore, because when official channels go quiet, unofficial ones get loud. The question is whether that noise contains signal or just echoes of anxiety in an information vacuum. Did the silence conceal actual data gaps the public could see, or was it all just the normal frustration of losing access during a shutdown? That's what we're digging into next. Part 3: Data Gaps, Redactions, and the Dead Zone. Let me introduce you to what I'm calling the Dead Zone. October 1st through 7th, 2025. 7 days when the most interesting interstellar object in years was at its most accessible point to our Mars orbiters, and when NASA's public communications apparatus was effectively shut down. Not offline, not censored, but administratively paused due to a lapse in federal funding. This is the zone where fact and speculation blur together, where the absence of information becomes information itself, and where pattern-seeking human minds start connecting dots that may or may not form a picture. Let's establish what counts as a real gap versus what counts as normal shutdown behaviour. During a government shutdown, NASA's web presence is supposed to go minimal. The main nasa.gov site might display only a closure notice. Mission-specific pages stop updating. The raw image browsers that usually populate with fresh data from Mars orbiters and rovers go static. The latest news feeds freeze. Social media accounts go silent. This is all documented in NASA's Continuity of Appropriations Plan, which is publicly available. The plan explicitly states that citizens won't have access to many web services during a lapse. It's not subtle about this. So if you were watching NASA's websites during the first week of October and noticed they weren't updating, that's not evidence of suppression. That's evidence of policy being followed exactly as written. But here's where it gets interesting. Not all space agencies shut down. The European Space Agency continued normal operations. Space.com, which is a private media outlet covering spaceflight, kept publishing stories. Amateur astronomy networks kept posting observations. Third-party satellite trackers continued updating orbital elements. So the dead zone wasn't universal. It was specifically a US government phenomenon, specifically NASA. This created an asymmetry in information flow. European sources were actively discussing 3I-ATLAS. American official sources were silent. That asymmetry looks like concealment even when it's just bureaucracy. Now let's talk about what would constitute an actual anomalous gap, something beyond normal shutdown protocol. Examples would include raw images that were scheduled to be posted based on pre-shutdown timelines but never appeared, telemetry data that showed up incomplete or with timestamps that didn't make sense, observation windows that were listed as planned in science schedules but produced no corresponding data products, spacecraft maneuvers that appeared in trajectory files but weren't explained in operations logs. These would be red flags, indicators that something beyond normal shutdown procedures was occurring. As of early October, when the shutdown was fresh and data pipelines were frozen, it was genuinely hard to tell the difference between policy-driven gaps and anomalous ones. Everything looked like a gap because nothing was being publicly released. I need to make something clear before we go further. There is no official evidence that 3I-ATLAS data from the Mars window was classified. Classification is a specific legal process. It requires authority, documentation, and justification under national security criteria. Nothing I've found suggests that classification orders were issued for scientific data about this comet. Speculation about classification is just that, speculation. It's important to state this clearly because once the idea of classified space data enters the conversation, it takes on a life of its own. People assume it must be hiding something dramatic, but the absence of evidence for classification is not itself evidence of transparency. It just means we're not dealing with formal secrets, we're dealing with informal silence. That said, the speculation was immediate and loud. YouTube channels dedicated to UAPs and anomalous phenomena latched onto 3I-ATLAS within days of the shutdown beginning. Reddit threads filled with claims. Some said raw image files from Mars Reconnaissance Orbiter were posted briefly and then pulled from archive servers. Others claimed that FITS files, which are the standard format for astronomical data, showed signs of redaction when examined at the pixel level. Still others insisted that spacecraft had performed unscheduled manoeuvres during the window, burns that appeared in telemetry but weren't explained in public-facing documentation. I'm presenting these as unconfirmed claims, not as facts. They're part of the story because they shaped public perception during the dead zone, but unverified internet claims are not evidence, they're hypotheses waiting for data. So how do you test these claims? How do you separate real anomalies from misunderstandings and fabrications? Here's a simple checklist you can use when data eventually gets released. First, check timestamps. Do the observation times match the planned windows that ESA and other sources discussed before the shutdown? If images or spectra were supposed to be taken on October 3rd during the closest approach, and they show up later with October 3rd timestamps, that's consistent. If they show up with different dates or no-date metadata, that's weird. Second, look at instrument mode notes. Every observation has metadata that describes how the instrument was configured, what filters were used, what exposure times were set. If multiple observers use different instruments but report similar results, that's cross-validation. If one observer reports something radically different, that's a red flag worth investigating. Third, cross-calibrate with ESA's public products. When Mars Express and ExoMars data get released, they should tell a consistent story with any NASA data. The comet's brightness, position, and activity level should match across independent observers. If they don't, someone made a mistake, or someone's data is incomplete. One thing to remember is that even NASA's own continuity plan acknowledges the website can be taken down entirely or reduced to a static page during a lapse. This sets expectations. Don't expect real-time updates. Don't expect the usual cadence of image releases. Expect batch releases after funding returns. That's normal. What wouldn't be normal is if, months after the shutdown ends, we still have no Mars window data from NASA assets, despite clear opportunity and capability. That would suggest either the observations didn't happen, which would be a missed scientific opportunity worth questioning, or they did happen and are being withheld, which would require explanation. I want to encourage skeptical patience here. The comet passes through solar conjunction from Earth's perspective around late October and into November. It becomes difficult or impossible to observe from ground-based telescopes during that period, but it re-emerges in late November and December. That reappearance offers a chance to validate any claims of anomalous behaviour during the Mars window. If people are claiming the comet did something strange in early October, brightened unexpectedly, showed unusual spectral features, or changed its trajectory, those effects should have ongoing consequences. The post-conjunction data will either support or refute those claims. Patience and attention to detail will give us answers that speculation cannot. So here's where we are. The dead zone existed. That's not controversial. NASA's public communications paused during the optimal Mars observing window due to the shutdown. That's documented fact. Speculation about missing or manipulated data emerged immediately. That happened, and it's part of the cultural story around this event. But actual evidence of data suppression, as opposed to normal shutdown-driven delays, has not been verified as of early October. The gaps we see are mostly policy-driven. Whether there are real anomalies hiding within those policy-driven gaps is something we'll only know when the data pipelines reopen and the batch releases begin. Until then, the dead zone remains what it is, a frustrating blank space in the timeline that could be completely innocent or could be concealing something worth a second look. And that uncertainty is exactly the kind of thing that drives people to ask the next logical question. Did the comet itself behave oddly, or is all of this just noise around a normal celestial event? Let's look at the trajectory math and see if the orbit tells us anything the silence doesn't. Part 4. Anomalous signals, Doppler shifts and orbital perturbations. We need to talk about the comet's path because this is where speculation meets mathematics, and mathematics doesn't care about government shutdowns or narrative. 3I-ATLAS is following a hyperbolic orbit. That's the first critical fact. Hyperbolic means it's not bound to the Sun. It came from interstellar space, it's swinging around our star, and it's heading back out, never to return. The orbital elements place perihelion, the closest point to the Sun, at approximately October 29th through 30th, 2025, at a distance of about 1.36 astronomical units. That's a bit farther out than Earth's orbit. On October 3rd, the comet passed within about 0.19 astronomical units of Mars, which translates to roughly 30 million kilometres. Those numbers come from orbit fits based on observations taken from Discovery in July through September, calculated by the Minor Planet Center and confirmed by JPL's Solar System Dynamics Group. Here's how orbital determination works in practice. Observers around the world, professional observatories and amateur astronomers measure the comet's position against the background stars. Each measurement gives you a right ascension and declination, essentially cosmic latitude and longitude, plus a timestamp. You collect dozens or hundreds of these measurements as the object moves across the sky. Then you fit an orbit, a mathematical model that predicts where the object should be at any given time based on the sun's gravity. If the observations match the predictions, your orbit is good. If there are residuals, differences between where you observed the object and where the model says it should be, you look for explanations. Maybe your measurements have errors. Maybe the object is accelerating due to forces other than gravity. Comets are famous for non-gravitational forces. When ice on a comet's nucleus heats up and sublimates, it jets away as gas, and that gas carries momentum. The nucleus experiences a tiny rocket effect. Depending on the spin state and the location of the active areas, this can nudge the comet's orbit in predictable or unpredictable ways. Astronomers model this with something called non-gravitational parameters, extra terms in the orbit equations that account for thrust from outgassing. For most comets, these parameters are small but measurable. They explain residuals of a few arcseconds over months of observation. For 3I-ATLAS, what we do have, as of early October, is Hubble Space Telescope imaging from July that constrains the nucleus size and confirms active dust production. The Hubble data gives an upper limit on the radius and shows a clearly developed coma, which means the nucleus is warm enough and volatile enough to produce gas and dust. That's consistent with cometary behaviour, not an inert rock. What we don't have, and this is critical, are peer-reviewed claims of anomalous Doppler shifts or unexpected delta-V events during the Mars window. Let me unpack that. Doppler shifts are changes in the frequency of light or radio signals caused by motion toward or away from the observer. If you're observing a comet and you measure its spectrum, absorption or emission lines will be shifted from their rest wavelengths by an amount that depends on the comet's velocity along your line of sight. If the comet suddenly accelerated in a way not explained by solar gravity or normal outgassing, you'd see an unexpected change in that Doppler shift. Similarly, if you're tracking the comet's position very precisely and you notice it's not where your gravitational model predicts, that's a delta-V event, a velocity change. Space telescopes and radar observatories can detect positional changes equivalent to accelerations of fractions of a millimetre per second squared over days or weeks. It's incredibly sensitive. As of early October, the public orbital solutions for 3I-ATLAS don't show signs of large unexpected accelerations. The Minor Planet Center's most recent orbit fits are consistent with a comet experiencing some level of non-gravitational force due to outgassing, which is normal. The orbital eccentricity remains hyperbolic, meaning it's leaving the solar system. There's no indication it's being deflected onto a bound orbit or ejected faster than physics would predict. Now, could there be subtle anomalies that haven't been published yet? Absolutely. Orbital refinement is an ongoing process. As more observations come in, especially after the post-conjunction reappearance, the orbit will be updated. If those updates reveal something strange that wasn't obvious in the preliminary fits, we'll see it in the published elements. The Minor Planet Center and JPL publish updates regularly, and their data is public. You can check it yourself. The ESA observation campaign with Mars Express and ExoMars aim to capture shape hints and brightness variations. At 30 million kilometres, even their best cameras wouldn't resolve the nucleus. What they could measure is how the brightness changes over time, which tells you about the rotation state and the shape. If the nucleus is elongated and tumbling, you get a periodic light curve. If the coma is asymmetric, maybe brighter on one side due to a localized jet, that shows up as a time-varying signal. These are exactly the kinds of observations that could reveal non-gravitational effects or structural oddities, but only after the data is analysed. As of the shutdown week, we hadn't seen ESA's results. That doesn't mean they found nothing. It means they haven't published yet, which is normal. Science takes time. Now let's address the popular claims circulating in less formal spaces. Some online discussions have suggested that military or classified space tracking assets detected unusual Doppler signatures during the Mars window. The US Space Force and other national security space entities do track objects. They have powerful radar and optical systems, but there's no public confirmation that any of these systems were tasked to observe 3I-ATLAS, and certainly no confirmation of anomalous findings. Treating these claims as anything more than speculation would be irresponsible without supporting evidence. I mention them because they're part of the cultural story, not because they're verified. If outgassing jets did produce small accelerations, where would they show up? In the orbit fits, as I mentioned, but also potentially in imaging. A bright jet on one side of the nucleus would create an asymmetry. Spectroscopy could detect the composition of the jet material, whether it's water, carbon monoxide, methane, or something else. Ground-based observers did obtain some spectra of 3I-ATLAS in July and August, and those showed features consistent with typical cometary volatiles. If something radically different was detected in October, we'd expect papers to start appearing by now, at least as preprints. As of early October, no such papers have surfaced. That suggests the preliminary answer is the comet is behaving like a comet. Here's my promise to you. After the post-conjunction observations in late November and December, after the Mars data gets publicly released, we'll revisit the orbital solutions. The Minor Planet Center will update their elements. JPL will update their Horizons database. If the orbit changed in unexpected ways during October, those updates will show it. If the mass estimate changes significantly, that'll show up too. If new spectroscopy reveals something bizarre, that'll be published. The scientific process is slow, but it's transparent. We'll have answers, and we'll compare them to the claims being made now. That's the test. If the anomalies people are worried about are real, they'll leave traces that survive peer review. If they're not real, the updated data will be boring, in the best possible way. So, what's the conservative view right now? Available measurements through September fit a cometary interpretation with normal activity levels. The hyperbolic orbit is consistent with an interstellar origin, which is exciting enough on its own. Claims of strange dynamics, unexpected accelerations, or military detections of odd signals remain undemonstrated in public, peer-reviewed literature. That doesn't mean nothing interesting happened. It means we don't yet have the evidence to say something definitely did. And that brings us to the next layer of speculation, because if the dynamics aren't the curveball, maybe the composition is. Let's talk about the metal. Part 5, the metal mass debate and the implications. Here's where 3I-ATLAS starts to get really interesting or really confusing, depending on your tolerance for uncertainty. We don't know how much this thing weighs. Let me explain why. That's a problem. The Hubble observations from July constrain the size of the nucleus using a model of the coma's brightness and dust production rate. The analysis suggests a nucleus diameter somewhere between 0.32 and 5.6 kilometers. That's a huge range, over a factor of 17 in diameter, which translates to an even bigger range in volume and mass. Why such uncertainty? Because we can't directly resolve the nucleus. It's too small and too far away. What Hubble saw was the coma, the cloud of dust and gas, and from that scientists have to work backwards to estimate how big the solid body at the centre must be. That requires assumptions about how reflective the surface is, the albedo, and how efficiently it's producing dust. Different reasonable assumptions give you different sizes. The Hubble team also estimated mass loss rates, how much material the comet is shedding per second. Their model suggests somewhere between 6 and 60 kilograms per second during the July observations. Again, a wide range, depending on the dust grain size distribution and other factors. This is consistent with an active comet. Comets lose mass as they approach the Sun. That's what makes them visible, the escaping gas and dust reflecting sunlight and fluorescing. So the mainstream interpretation, based on what's been published in preprints, is that 3I-ATLAS is a comet. It has a nucleus made of some combination of ice and rock. It's outgassing. It's behaving like comets behave. Nothing about the Hubble data demands a different explanation. But then there are the speculative claims, and these are where things get spicy. Some analyses, published in less formal venues or discussed in media interviews, have suggested mass estimates for 3I-ATLAS in the tens of billions of tons. For context, that's much heavier than you'd expect for a typical comet nucleus of the estimated size. A comet nucleus with a diameter of a few kilometers and a density like ice and rock, say 500 to 1,000 kilograms per cubic meter, would mass in the range of billions of tons, not tens of billions. To get to tens of billions, you need either a much larger nucleus or a much denser one. If the nucleus is on the small end of the size estimate but still that massive, it would have to be very dense. And dense means metal. There have also been reports of nickel emission lines in the coma. Let me be clear about what this means and what it doesn't. Nickel is a metal, yes, but it's not unusual to find metals in cometary comae. Astronomers have detected iron, nickel, magnesium, sodium, and other metals in the gas surrounding comet nuclei. This happens because comets contain dust grains that include silicates and sometimes metal-bearing minerals. When the sun heats the nucleus and gas flows off, it carries tiny dust particles. Those particles get hit by sunlight, heat up, and can release metal atoms. The Very Large Telescope and other observatories have found nickel in solar system comets, including some that were studied intensively. So detecting nickel in 3I-ATLAS wouldn't, by itself, prove anything exotic. However, if the nickel lines were unusually strong, or if the abundance ratios were off compared to typical cometary chemistry, that would be interesting. It might suggest the object formed in a different chemical environment, perhaps around a different kind of star, or perhaps it's a fragment of something that underwent differentiation. Differentiation is the process where a planetary body melts, and the heavy metals sink to the core. If a planet or large asteroid formed, differentiated, and then was shattered by a collision, you could get chunks of nearly pure metal floating around. There are metallic meteorites in our own solar system, pieces of the cores of shattered planetesimals. Could 3I-ATLAS be an interstellar version of that? It's not impossible, but it's highly speculative without detailed spectroscopy confirming an unusual composition. Let's think through the possibilities if 3I-ATLAS were genuinely metal-rich. What origins would fit? One option is a fragment from a disrupted exoplanet or large asteroid, something that formed around another star, differentiated, and was blasted apart, with this piece wandering into interstellar space. Another option is a fragment from a stellar collision or supernova remnant, though that seems less likely because such environments are violent and would probably vaporize or heavily process anything solid. A third, and this is where things get wild, is that it's engineered. A probe, a derelict spacecraft, a piece of megastructure. I want to be very clear. There is no consensus in the scientific community that supports a technological origin. None. The detection of nickel or a high mass estimate does not equal proof of artificiality. But the combination of unknowns, the mass uncertainty, the composition questions, and the timing of the Mars window during the shutdown creates a space where speculation thrives. If 3I-ATLAS were dense and metal-rich, the strategic implications would be significant even without invoking technology. A large metallic object passing through the inner solar system would be of immense interest for resource utilization concepts. There's serious discussion in aerospace and mining industries about capturing and utilizing asteroids for their metal content. An interstellar object, even if you couldn't capture it because it's on a hyperbolic trajectory, would be a scientific goldmine. You'd want every instrument you have pointed at it. You'd want samples if remotely possible, which it's not with current technology, but you'd at least want exhaustive remote sensing. So if there were indications this thing was unusual in composition, that could explain a heightened level of interest, even classified interest, from certain parties. That's speculation, but it's grounded speculation. Now, here's the psychology angle. A big unknown during a quiet week is perfect fuel for theories. Human beings are pattern seekers. When official channels are silent, we fill the void with narrative. The shutdown created that void. The extraordinary nature of an interstellar visitor amplified the stakes, and the uncertainty about mass and composition, which is genuinely present in the scientific data, provided the raw material for more elaborate ideas. I'm not dismissing curiosity. I'm contextualizing it. The questions being asked are not unreasonable. The problem is that we don't yet have the answers, and in the absence of answers, some people jump to conclusions. What would falsify the metal monster hypothesis? Several things. If further observations tighten the size estimate and the albedo in a way that brings the mass down to normal cometary values, that would do it. If spectroscopy shows composition consistent with ices and typical silicate dust, that would weaken the metal case significantly. If the non-gravitational acceleration parameters, once refined, match what you'd expect from water or carbon monoxide outgassing. That supports a normal comet interpretation. If the light curve shows variation consistent with an irregular, fluffy, low-density body, rather than a compact, dense one that also points away from metal, these are all testable. We just need the data. The important thing to remember is that absence of evidence is not evidence of anything except our current ignorance. We don't have definitive proof. 3I-ATLAS is a normal comet. We also don't have definitive proof it's anything else. The Hubble data are consistent with a comet but don't rule out other possibilities within the uncertainty ranges. The trajectory is consistent with a comet experiencing mild outgassing, but doesn't rule out a denser object with weaker activity. We're in a frustrating middle ground, scientifically speaking, and that middle ground, combined with the communication dead zone during the Mars window, is why this story has legs. If 3I-ATLAS were truly unusual in mass or composition, what would it mean for our understanding of interstellar objects? It would suggest that the population of things drifting between stars is more diverse than we thought. Not just icy comets and rocky asteroids, but potentially fragments of catastrophically destroyed worlds, core material, maybe even processed or manufactured items. That would be huge. It would change how we think about interstellar space. Instead of mostly empty with occasional pristine planetesimals, it might be a graveyard of shattered systems, a museum of cosmic violence, or, in the most speculative case, a highway with travellers, intentional or derelict. But we're getting ahead of the data. The next step is to see what the post-shutdown releases show. Does the mass estimate tighten? Does the spectroscopy clarify composition? Does the orbit tell a boring or interesting story? Those are the questions that will matter in the coming months. So here's the promise I'm making. If data emerges that fundamentally changes our understanding of 3I-ATLAS, we'll revisit every claim being made now. The metal hypothesis, the mass estimates, the resource angle, and yes, the artifact angle, as uncomfortable as that might make some people. Science advances by testing ideas, not by dismissing them out of hand, but it also advances by proportioning belief to evidence. Right now, the evidence is thin and the uncertainty is wide. That's honest, that's where we are. And if you're frustrated by that, welcome to the scientific process. It's slow, it's messy, and it doesn't care about our desire for immediate answers, but it does eventually deliver truth, or at least gets us closer to it. Next, we need to talk about who could keep secrets if there were secrets to keep. Because if data were sensitive, the mechanism for suppression is as important as the motivation. Let's talk about agency politics and classified projects. Part 6. Internal friction, agency politics and classified projects. To understand how information can be controlled, you need to understand how government space operations actually work during a shutdown. Let me walk you through the bureaucratic machinery, because it's less dramatic than conspiracy theories imagine, but potentially more effective. NASA operates under something called the Continuity of Appropriations Plan, which is legally required whenever there's a lapse in federal funding. The plan is detailed. It specifies which employees are furloughed, which are accepted, and what activities continue. The categories are strict. Accepted activities include protection of life and property. That means the International Space Station, absolutely. Flight controllers keep the crew safe. Satellite operations that prevent loss of expensive assets, or that protect critical infrastructure, those continue too. Public communications, not accepted. Website updates, not accepted. Social media, not accepted. Press releases, not accepted. You see the pattern. What this means in practice for Mars orbiters is that flight operations teams can work if necessary to keep the spacecraft safe. If Mars Reconnaissance Orbiter needs a maneuver to avoid debris, even hypothetically, that happens. If there's a thermal issue or a communications problem, the team addresses it. But science planning, the meetings where researchers decide where to point cameras and when, those can slow down or stop because that's not life and property. Public data releases, those definitely stop because web administrators and public affairs specialists are furloughed. So you end up with a situation where spacecraft can operate, data can be collected, but the normal flow of information to the public is dammed up. It's not a conspiracy, it's administrative procedure. But the effect is the same: silence. Now let's talk about the civil-military interface, because this is where things get murkier. The Department of Defense, National Reconnaissance Office, and Air Force Research Laboratory maintain constant space domain awareness. They track everything in orbit and many things beyond. They have optical telescopes, both ground-based and space-based, that are arguably more powerful than anything NASA operates for science. They have radar systems that can track objects millions of kilometers away, and they don't publish their observations. That's not sinister, it's their mission. They're protecting national security space assets, monitoring potential threats, and maintaining situational awareness. If 3I-ATLAS passed through a volume of space they're monitoring, which it almost certainly did, they would have tracked it. They might have collected optical imagery, radar profiles, maybe even spectroscopy, depending on the asset. Would they share that data publicly? Almost never. Would they share it with NASA scientists? Maybe. Through back channels, if there were a scientific or safety reason. But it wouldn't be announced. The framework for interagency data sharing exists. NASA and the Department of Defense collaborate regularly on space situational awareness. Orbital elements for satellites and debris are shared. If a commercial satellite is at risk of collision, data flows between agencies to solve the problem. This cooperation is routine and mostly invisible to the public. Could it continue during a NASA shutdown? Absolutely. The military side doesn't shut down. Their funding continues under separate appropriations. So if military sensors were observing 3I-ATLAS and flagged something unusual, that information could flow to accepted NASA personnel, the flight controllers and mission safety staff who are still working, without ever entering the public communication pipeline that's been shut off. You could have a situation where data exists, where decisions are being made based on that data, and where the public hears nothing, all within perfectly legal frameworks. Not because of conspiracy, but because of jurisdiction and funding law. ESA's transparency during the same period highlights the divergence. The European Space Agency continued normal operations. They published updates. Scientists gave interviews. When asked about 3I-ATLAS, they talked openly about their observation plans. Space.com ran articles quoting mission scientists by name. This created a narrative asymmetry. Europe looked open, America looked silent. But the reason for America's silence was the Anti-Deficiency Act and the Continuity Plan, not a deliberate decision to hide scientific findings. Or at least, that's the most straightforward explanation. The alternative is that the shutdown provided convenient cover for withholding information that would have been withheld anyway. Distinguishing between those two scenarios requires evidence we don't have access to yet. Let me explain the Anti-Deficiency Act more clearly, because it's the legal backbone of all this. The Act, originally passed in 1884 and amended several times since, prohibits federal employees from spending or obligating funds that haven't been appropriated by Congress. Violating it is a felony. During a funding lapse, agencies have to determine which activities fall under exceptions, primarily life and property protection. Those determinations are documented. Agencies submit their plans to the Office of Management and Budget. Employees who work during a lapse on accepted activities get paid retroactively when funding returns. Employees who work on non-accepted activities, even accidentally, are breaking the law. This creates enormous caution. Managers furlough people liberally to avoid any appearance of violating the Act. The result is that even activities that might seem important, like updating a website to inform the public about an interstellar visitor, get shut down because they're not legally accepted. Now consider the political optics. NASA's continuity plan actually states, in plain language, that citizens won't have access to nasa.gov or NASA TV during a lapse. That's on page 7 of the 2024 version of the plan, publicly available as a PDF. The agency's telling you in advance that they're going to go dark. So when they do go dark, it's not a surprise and it's not evidence of wrongdoing. But here's the problem. Most people don't read continuity plans. Most people don't think about the Anti-Deficiency Act. What people see is that something extraordinary is happening in space, and NASA is silent. That gap between legal procedure and public perception is where conspiracy narratives grow. If something unexpected did appear during the Mars window, which chain of authority would decide what gets shared? That's a critical question. If a NASA spacecraft observed something anomalous, the data would first go to the mission science team. But if those scientists are furloughed, who's looking at the data? The accepted operations staff, the flight controllers. Their job is spacecraft safety, not science analysis. If they saw something in a raw image that seemed odd, would they even know what they're looking at? Would they have the authority to call in furloughed scientists? Maybe, if it posed a safety issue. But if it's just scientifically interesting, not safety critical, it might sit in a queue until the shutdown ends. Alternatively, if military sensors saw something, the decision chain goes through defense and intelligence agencies. Those decisions are classified by default. The public wouldn't hear about it unless there were a policy decision to declassify and release. Those decisions can take months or years. The ESA observation campaign, which was publicly announced and openly discussed, gives us a baseline. Space.com published articles on September 28th and October 1st, interviewing scientists about the planned observations. That's transparent. If NASA had similar plans, we didn't hear about them. But again, that could be purely because the public affairs infrastructure was shut down. Scientists might have wanted to talk. The administration might have planned observations. But without public affairs staff to facilitate interviews or write press releases, it doesn't happen. Not can't happen for legal reasons, just doesn't happen because the mechanism is offline. So what's the bottom line on internal friction and agency politics? NASA operates under strict legal constraints during shutdowns that silence public communications even when operations continue. The civil-military interface allows for data sharing that the public never sees. ESA's openness created a contrast that made NASA's silence look more suspicious than it might be. And if something genuinely unusual appeared, the decision-making chain for what to release would involve multiple agencies, potentially including classified entities, complicating and slowing any public disclosure. None of this proves anything was hidden, but all of it explains how something could be hidden, even unintentionally, within the normal functioning of bureaucracy. And that possibility, that things could be hidden not by evil intent but by procedure, is almost more unsettling than a conspiracy. Because you can fight a conspiracy, but fighting a bureaucracy is like punching fog. Meanwhile, there's another question we haven't addressed. Who else was watching quietly, with capabilities we don't usually hear about? Let's talk about alternate observers and black budget eyes. Part 7. Alternate observers and black budget eyes. NASA and ESA aren't the only players with eyes on the sky, and it's important to map the full roster of potential observers, because each one adds a thread to this story. Let's start with the ones we know about publicly. ESA's Mars Express and ExoMars Trace Gas Orbiter were actively tasked, as we've discussed. But ESA also operates JUICE, the Jupiter Icy Moons Explorer, which launched in April 2023 and is currently in the inner solar system on its way to gravity assists. According to planning documents and some preprint discussions, JUICE had a potential observing opportunity for 3I-ATLAS in November 2025, constrained by thermal and pointing limitations. That's after perihelion, but still potentially valuable for post-perihelion activity measurements. Then there's China's Tianwen-1, which has been orbiting Mars since February 2021. China's space program is less transparent than ESA's, but Tianwen-1 has cameras. Did they observe the comet? We don't know. They haven't announced observations, but absence of announcement doesn't mean absence of observation. There's also been discussion in the planetary science community about the Psyche mission's trajectory. Psyche is a NASA mission that launched in October 2023, headed for the metal-rich Asteroid 16 Psyche. Some preprints explored whether Psyche's cameras could be opportunistically pointed at 3I-ATLAS during its cruise phase. The geometry was discussed as potentially favourable for certain dates. Whether that happened is unclear. Psyche's primary mission is the asteroid, not comet observations, but spacecraft have been used for targets of opportunity before. It's plausible, but unconfirmed. Now let's talk about the observers that don't publish. Ground-based radar systems operated by the military and intelligence community can track objects in deep space. The most powerful of these is the Space Fence, operated by the US Space Force, which is an S-band radar on Kwajalein Atoll in the Marshall Islands. Space Fence is designed to track satellites and debris in Earth orbit, but in principle, radar can detect objects much farther away if they're large enough, and the radar is powerful enough. Could Space Fence or other classified radar systems have gotten a return from 3I-ATLAS? It's not impossible, but it's unlikely. The comet was tens of millions of kilometers away during the Mars window. Radar sensitivity drops with the fourth power of distance, so you need a very large target or an absurdly powerful radar. For context, planetary radar systems like Arecibo, Rest in Peace and Goldstone could detect near-Earth asteroids out to a few million kilometers under good conditions. 3I-ATLAS was 10 times farther during the Mars window. Radar detection seems improbable, but I can't rule it out entirely. Classified optical telescopes are another story. The National Reconnaissance Office operates space surveillance telescopes that are believed to be comparable to, or better than, the best civilian instruments. The logic is simple. If you can build a Hubble, you can build a spy satellite with similar optics pointed down instead of up. In fact, NRO donated 2 Hubble-class telescopes to NASA in 2012, hardware they had sitting around. If NRO has those capabilities, and they do, they could point them at 3I-ATLAS, would they? That depends on whether the comet was deemed a priority. Tracking foreign satellites, monitoring launches, and supporting intelligence operations would take precedence. But if someone with sufficient authority requested observation, or if automated tracking systems flagged the comet as anomalous, data could exist in classified channels. We wouldn't hear about it. That's the definition of classified. No public release, no confirmation, no data sharing with civilian scientists unless it goes through official declassification processes that take years. Let me be clear about something, because this is where speculation often goes off the rails. The rumours circulating online about military intercepts or classified imaging of 3I-ATLAS are unverified. I've seen claims on YouTube and Reddit that defence assets detected unusual signatures, that there were emergency tasking orders, that data was immediately classified. None of that has a verifiable source. No documents have leaked. No whistleblowers have come forward with credible evidence. These are stories, narratives built on the foundation of what's possible, rather than what's proven. I'm mentioning them because they're part of the cultural phenomenon around this event, not because they meet any standard of evidence. Why wouldn't black-budget censors publish their findings even if they found something extraordinary? Several reasons. Capability protection is paramount. If you reveal what your censors can see, you reveal their capabilities, and that helps adversaries understand what they need to hide. Mission secrecy is another factor. Intelligence collection missions are classified not just because of what they find, but because of where they're looking and how. Publishing an observation of 3I-ATLAS might inadvertently reveal orbital parameters of a spy satellite or the sensitivity threshold of a telescope. And finally, prioritization. Defense and intelligence agencies have specific missions. Satisfying public curiosity about a comet isn't one of them. Even if data exists, there's no institutional incentive to release it and plenty of reasons not to. This creates data asymmetry. ESA openly discussed their plans and will eventually release data. NASA was silent due to the shutdown but will likely release data post-shutdown. Military and intelligence assets may or may not have data, and if they do, we'll probably never see it. That asymmetry creates an illusion of capture, a sense that someone knows more than they're saying, which is probably true but not necessarily sinister. Different organisations have different mandates. Not everything is meant to be public. Here's a litmus test we can apply later. ESA datasets, when released, will include timestamps, instrument settings, and observational metadata. NASA datasets, when released, will have the same. If both agencies observe the comet during overlapping time windows, their data should tell a consistent story. The comet's brightness, position, and spectral features should match within measurement uncertainty. If they do match, that's strong evidence against any major anomaly being suppressed. If they don't match, or if one agency's data shows something radically different, that's a red flag worth investigating. Cross-checks like this are how you test for consistency and honesty in science. The same principle applies to orbital solutions. The Minor Planet Center aggregates observations from observers worldwide and publishes updated orbital elements. Those elements are fit to all available data. If NASA's Mars orbiters contributed observations that change the orbit fit significantly, we'll see it in the MPC updates. If they didn't contribute data, or if their data is withheld, the orbit fit will be based only on ground and easy observations. That's still useful, but it's incomplete. The high-rise resolution question is worth revisiting in this context. Some speculation has centred on the idea that HiRISE could have resolved structures on the nucleus, maybe seeing evidence of artificiality. Let's do the math again. HiRISE's best resolution at the Martian surface, from typical orbit altitude, is about 30 centimetres per pixel. The comet was 30 million kilometres away. At that distance, HiRISE's angular resolution of 1 microradian translates to about 30 kilometres per pixel, not 30 centimetres. You're not resolving surface details. You're barely resolving the nucleus at all, even if it's several kilometres across. What you can measure is brightness and how it changes, which tells you about shape and activity. But the idea that HiRISE could have photographed a structured object and seen panels or engines or antennae, That's not consistent with the geometry. If there was something to see at that level of detail, you'd need to be much closer. This doesn't mean HiRISE wasn't tasked. It means expectations should be calibrated to what's actually possible. The promise I'm making to you is this. When ESA releases their Mars window datasets, whenever that happens, we'll examine them. When NASA releases whatever they collected, if they collected anything, we'll compare. If the Minor Planet Center updates orbital elements after incorporating October observations, we'll look at whether the fit changed significantly. These are the checkpoints that will expose gross anomalies regardless of who observed what. Science is self-correcting in the long run because independent observers eventually force consistency. Contradictions become obvious. So even if classified assets saw something, and even if that data stays classified, the public record should eventually converge on a coherent picture. If it doesn't converge, that's when the questions get serious. Until then, we track what's trackable, we note the gaps, and we wait. But let's entertain a different angle for a moment. What could the Mars proximity itself have revealed or changed? Were there hidden opportunities or effects during that close passage that we should be thinking about? Let's explore the Mars proximity effect. Part 8. The Mars proximity effect. Hidden opportunities and adjustments. When an interstellar object passes within 30 million kilometers of a planet, things can happen. Not dramatic things like capture or collision at that distance, but subtle interactions that might be scientifically revealing or, in more speculative scenarios, strategically interesting. Let's start with the straightforward physics. Mars has gravity. At 30 million kilometers, the gravitational influence is tiny, but it exists. You can calculate the tidal effects and orbital perturbations. For an object the estimated size and mass of 3I-ATLAS, the effect of Mars's gravity at closest approach would be measurable in principle, a slight deflection, but small. Astrometry. Precise position measurements could potentially detect it. This is actually useful because if you measure the deflection and know Mars' mass, you can constrain the comet's trajectory more precisely. It's a natural experiment in orbital mechanics. Then there's the space environment around Mars. The planet has a weak magnetic field, remnants of an ancient dynamo, and a thin atmosphere that extends in a diffuse exosphere far above the surface. Mars also sits in the solar wind, the stream of charged particles flowing from the Sun. When the solar wind hits Mars, it interacts with the upper atmosphere and the weak magnetic fields, creating a bow shock and a magnetotail. If 3I-ATLAS passed through or near these structures, which it didn't at 30 million kilometers, but let's consider the principle, you could see interactions between the comet's coma and the Martian space environment. The coma is full of ions, charged particles. In a strong enough field or plasma environment, those ions would be deflected, maybe producing a visible tail distortion or a brightening from increased excitation. ESA's instrument goals reflect awareness of these possibilities. Mars Express carries HRSC, the high-resolution stereo camera, which can take wide-angle images useful for detecting shape or brightness variations. ExoMars TGO has CASIS, the colour and stereo surface imaging system, and NOMAD, the nadir and occultation for Mars discovery spectrometer. NOMAD can measure atmospheric composition and, with careful pointing, could attempt spectroscopy of the comet's coma. What would they be looking for? Changes in gas production rate, spectral lines from different molecules, asymmetries in the coma that might indicate jet activity. At 30 million kilometers, the resolution isn't fine, but you can still characterize the overall behavior. What you can't see are fine details. You can't see thrusters if it were a spacecraft. You can't resolve surface structures if the nucleus is small. The best you can do is brightness versus time, color in different filters, and maybe coarse spectroscopy. If the comet experienced an outburst, a sudden increase in activity, that would show up as a brightness spike. Outbursts happen on comets when a fresh patch of ice is suddenly exposed to sunlight, or when a cliff collapses and releases trapped gas. They're dramatic but natural. Detecting an outburst during the Mars window would be interesting, but not necessarily anomalous. Now, let's consider a solar wind angle. Space weather varies. The Sun constantly emits the solar wind, but the density and speed fluctuate. Coronal mass ejections, or CMEs, are eruptions of plasma and magnetic field from the Sun that can race through the solar system. If a CME hit 3I-ATLAS near the time of the Mars window, it could spike activity. The increased particle flux would heat the nucleus more. potentially increasing gas production. The comet would brighten temporarily. This is documented behaviour for solar system comets. After a CME impact, you sometimes see a brightness increase lasting hours to days. If 3I-ATLAS brightened during the Mars window, and if a CME was present in the data from solar monitoring spacecraft like SOHO or STEREO, that would explain the brightening without invoking anything exotic. Correlation isn't causation, but in this case, causation is plausible. I don't have specific CME data for early October 2025 at hand, but it's checkable. Solar data is public and archived. Here's a fun, highly speculative what-if. Could any Mars orbiter have collected dust particles from the comet's tail? The coma extends outward from the nucleus as gas and dust. The dust particles are tiny, microns to millimeters, and they spread along the comet's trajectory. At 30 million kilometers, the particle density would be extremely low, but non-zero. If an orbiter happened to fly through the extended coma or tail, and if it had dust detectors, it might capture grains. This is how the Stardust mission worked, intentionally flying through a comet's coma to collect samples. Mars orbiters aren't designed for this, but they do have surfaces. In principle, dust could impact and stick. Analysing that dust later, if you could somehow retrieve it, would be the ultimate prize: physical samples from an interstellar object. Realistically, this didn't happen. The geometry was wrong, the particle density too low, and none of the Mars orbiters have sample return capability anyway. But it's a fun thought experiment and illustrates what might be technically possible with future missions. MAVEN, the Mars Atmosphere and Volatile Evolution Orbiter, is sensitive to the solar wind and the Martian upper atmosphere. Its instruments measure plasma properties, magnetic fields and energetic particles. If the solar wind conditions change significantly during the Mars window, MAVEN would detect it. If there were an indirect effect from the comet's presence, say the coma releasing ions that propagated through interplanetary space and somehow perturbed Mars's space environment, MAVEN might see that. This is extremely speculative and probably physically negligible given the distances, but MAVEN data could provide context for space weather during the relevant time period. If scientists later correlate MAVEN measurements with comet activity, that could make for interesting papers about large-scale solar system interactions. The current best-fit expectation from the scientific community is that nothing dramatic happened. Comets near Mars aren't unusual in principle, though interstellar ones are rare. The physics doesn't predict any wild interactions at 30 million kilometers. What we expect is that the comet continued on its trajectory, outgassing normally, and the Mars orbiters collected photometry and maybe spectroscopy. The data, when released, should show a comet being a comet. If it shows something else, that's when things get interesting. But jumping to anomalies before seeing the data is premature. Here's a caution against overfitting. Humans are pattern recognition machines. If you see a small wiggle in a light curve, it's tempting to interpret it as significant. Maybe the comet rotated and brought a brighter patch into view. Maybe there was a micro outburst. Maybe the measurement had noise. A wiggle isn't evidence of spacecraft maneuvering. It's just a wiggle until you understand it. This is why peer review matters. Scientists look for alternative explanations before claiming discovery. The public, understandably, is less patient. When speculation fills the void, every wiggle becomes a signal. My promise, again, is to revisit this with post-conjunction analyses. If NASA or ESA scientists publish papers about the Mars window observations, we'll read them. If there were brightness changes, spectral features, or anything else noteworthy, it'll be in the literature. If the comet was boring, we'll know that too. And boring in this context is actually kind of reassuring. It means the universe is behaving as expected. Which brings us to an uncomfortable question. If there were secrets, how exactly do you hide a space mystery from a global scientific community and a public that's increasingly skeptical of official narratives? Let's talk about silencing mechanisms. Part 9. The silencing mechanism. How do you hide a space mystery? If you wanted to hide a discovery about 3I-ATLAS, how would you actually do it? Not in a movie, where shadowy figures pull fire alarms and confiscate hard drives, but in reality, where bureaucracy is the weapon and plausible deniability is the shield. Let's walk through the mechanisms that produce silence, both the legal ones and the more troubling hypotheticals. Start with shutdown rules, because they're real and they're effective. We've covered this, but it's worth reiterating. During a government shutdown, NASA's public affairs infrastructure stops. Websites don't update, not because someone's ordered them not to, but because the people who update them are furloughed and legally prohibited from working. Press releases don't go out because public affairs specialists aren't there to write them. Social media goes quiet because the accounts are unmonitored. This is procedural silence, not intentional suppression. But the effect is the same. The public hears nothing. And here's the key. This silence is predictable and legal. NASA's continuity plan says it will happen. So if you were someone who wanted certain information to remain quiet, a shutdown is incredibly convenient. You don't have to order silence. You just let procedure take its course. Now let's distinguish between embargo and classification, because these are different and often confused. An embargo in science is when researchers agree to withhold findings until a certain date, usually to coordinate with a journal publication. This is standard practice. You don't want data leaking piecemeal before the peer-reviewed paper comes out, because it undermines the review process and can lead to misinterpretation. Embargoes are temporary and voluntary. Classification is a legal restriction. Classified information is protected by law from unauthorized disclosure. Revealing it can result in criminal charges. Classification requires authority, usually from the executive branch under national security justification. It has specific categories: confidential, secret, top secret. It requires proper handling, storage, and clearance levels for access. These are not the same thing. A scientific embargo doesn't prevent you from talking about findings. It's professional courtesy. Classification makes it illegal to talk. Don't conflate them. Are there precedents for data delays during past shutdowns? Absolutely. Every time the government shuts down, NASA's data pipelines slow or stop. Mars rover images that would normally be posted within days sit in queues. Hubble data releases are postponed. Mission websites freeze. This is documented and happens every single time. The 2018 to 2019 shutdown lasted 35 days and caused significant delays across multiple missions. Scientists complained publicly about lost productivity and delayed publications. That's the norm. So delays in 3I-ATLAS data releases, if they occur, would be consistent with pattern, not evidence of special treatment. But here's where it gets interesting. Format barriers. Most people don't realize that raw astronomical data isn't just images you can open in a photo viewer. It's in specialized formats like FITS, Flexible Image Transport System, which requires specific software to read. The files are huge and contain not just pixel values, but extensive metadata about instrument settings, calibration, timestamps, pointing coordinates. Analyzing this data requires expertise. You need to understand the instrument, the calibration process, the sources of noise and artifact. This creates a natural barrier to public scrutiny. Even if NASA dumps all the raw data publicly tomorrow, most people wouldn't know what to do with it. Only a small community of specialists could properly analyze it. That's not sinister, it's just technical reality. But it does mean that even open data isn't truly open to the general public. You need expertise to extract meaning. Compartmentalization is a real phenomenon in large organizations, especially those with classified or sensitive programs. Different teams work on different pieces of a project. Not everyone sees the whole picture. In intelligence work, this is deliberate. It limits damage if someone leaks or is compromised. In civilian science, it's more accidental, a consequence of specialization. The people operating the Mars orbiters aren't the same people doing orbital dynamics calculations, who aren't the same people doing spectroscopic analysis. If something unusual showed up in one dataset, the person who first saw it might not even recognize its significance. They'd note it, maybe flag it for a specialist, but information flow between groups can be slow. During a shutdown, with people furloughed and communication disrupted, compartmentalization becomes even more pronounced. You could have a situation where data exists, someone saw something odd, but the person who could interpret it is furloughed, and the information doesn't propagate. Not conspiracy, just organizational friction. True whistleblower evidence would look different from speculation. It would be emails, memos, or logs. It would have names, dates, and specifics. It would be verifiable through cross-referencing or corroboration. As of early October 2025, no such evidence has surfaced publicly regarding 3I-ATLAS. No documents have been leaked to journalists. No former employees have come forward claiming suppression. That doesn't mean it didn't happen, but absence of leaks is notable. In the age of digital communication and widespread mistrust of government, secrets are hard to keep. They leak. We've seen this with classified programs, with Pentagon UFO documents, with intelligence failures. Leaks happen. If there were a smoking gun about 3I-ATLAS, I'd expect someone, somewhere, to have leaked it by now. The fact that hasn't happened suggests either there's nothing to leak, or the circle of people who know is incredibly small, or we're still in the early stages and leaks take time. Time will tell. Here's a skeptic's toolkit you can use when data starts coming out. First, check file integrity. FITS files have checksums. If someone modified a file after it was created, you can detect it. Second, examine timestamps. Observation time should match expected windows. If images are stamped at times when the comet wasn't visible from that spacecraft's position, something's wrong. Third, look at instrument housekeeping data. Every observation comes with metadata about the spacecraft's status, pointing direction, temperature, power levels. Anomalies in housekeeping can reveal whether an observation was routine or unusual. Fourth, cross-check with other missions. If ESA and NASA both observed the comet at overlapping times, their results should be consistent. Discrepancies demand explanation. This isn't paranoia, it's good science. You trust but verify. A global cover-up across ESA, NASA, and the Minor Planet Center would leave inconsistencies in orbital fits. Here's why. The orbit is determined by fitting a model to observations from multiple sites over time. If someone withheld observations or falsified them, the fit would be worse. Residuals would be larger. Other observers, amateurs included, have been tracking 3I-ATLAS. Their observations are independent and publicly contributed to the Minor Planet Center. If the official orbit didn't fit the amateur data, people would notice. The MPC publishes residuals. You can check how well the model fits each observation. A conspiracy would require coordination across multiple countries, agencies, and independent observers. That's implausible. Information wants to be free, as the saying goes, especially in science where reputations are built on openness and discovery. So let's reiterate the core message. Silence does not equal suppression, but the optics invite suspicion. When official channels are quiet during an extraordinary event, people assume the worst. That's human nature, and it's precisely that assumption, that narrative instinct, that gives this story its power. We want there to be a mystery. We want the shutdown to mean something more than budget politics. We want the comet to be unusual because ordinary is boring. I'm not immune to that desire. None of us are. But desire doesn't make truth. Evidence does. And right now, the evidence for active suppression of 3I-ATLAS data is thin to non-existent. What we have is procedural silence, technical barriers, and organizational friction, all of which are real but mundane. The question is whether mundane explanations are sufficient, or whether something more is hiding in the gaps. To answer that, let's stack up the competing hypotheses and see which ones hold up under scrutiny. Part 10. 6 competing hypotheses. Let's organize the chaos. I'm going to present 6 hypotheses that attempt to explain what happened or didn't happen during the Mars window in early October 2025. For each one, I'll lay out the core claim, the evidence that supports it, and critically, what would falsify it. Because a hypothesis that can't be disproven isn't science, it's just storytelling. Here we go. Hypothesis 1. Bureaucratic coincidence. The shutdown explains the communications gaps. NASA's Mars assets either didn't observe the comet, or they did, and the data is sitting in a queue waiting for post-shutdown processing. ESA ran their campaign as announced. The comet behaved like a comet. Everything will align when data is finally released. This is the null hypothesis, the boring explanation. It requires no special pleading, no conspiracy, no exotic physics. It's consistent with how government shutdowns work and how science normally proceeds. The supporting evidence is NASA's continuity plan, which explicitly says public communications pause during funding lapses. ESA's open discussion of their plans, the absence of any verified leaks or whistleblower claims. How do you falsify this? If ESA releases data and the Minor Planet Center updates orbital elements, and those updates contradict prior predictions in significant ways, that would be a red flag. If NASA's eventual data release shows the comet in locations or states inconsistent with ESA's observations during the same time windows, that's a problem. If amateur observers who track the comet independently report brightness, or position anomalies that don't appear in official datasets that suggest selective reporting. The key test is consistency. If all observers, public and private, tell the same story, hypothesis 1 wins. Hypothesis 2, massive metallic core. 3I-ATLAS has a nucleus on the large end of the size estimates with unusually high density, possibly metal-rich. This would put its mass at the higher end of speculative estimates, tens of billions of tons. Nickel emission lines in the coma are stronger than typical comets, suggesting the nucleus is enriched in metals compared to normal icy rocky compositions. This hypothesis is speculative but not impossible. Metal-rich asteroids exist in our own solar system. A fragment from a disrupted differentiated body around another star could plausibly wander into interstellar space. The supporting evidence, such as it is, comes from early reports and blog discussions, particularly those amplified by Avi Loeb and outlets like The Debrief, discussing unusual mass-to-size ratios and nickel detections. The problem is these aren't peer-reviewed findings. They're preliminary, often based on incomplete data or aggressive interpretations. How do you falsify this? Tighter constraints on nucleus size and albedo that bring mass estimates down to normal cometary ranges. Spectroscopy showing composition dominated by water ice, carbon monoxide, and typical silicate dust with metal abundances consistent with solar system comets. Non-gravitational acceleration parameters that match what you'd expect from volatile outgassing, not high-mass inert behaviour. If the comet's light curve shows rapid variation consistent with a fluffy, irregular, low-density body tumbling that argues against a dense metal core, the post-perihelion data will be critical here. If brightness and activity continue to match a normal comet through perihelion and beyond, the metal hypothesis loses steam. Hypothesis 3, engineered or technological artifact. This is the big one, the idea that 3I-ATLAS is not natural, that it's a probe, derelict, or piece of technology from another civilization. This would manifest as non-gravitational maneuvers that don't correlate with outgassing, structured light curves showing geometric rather than natural rotation, spectral signatures inconsistent with known cometry or asteroidal materials, or radio emissions that are coherent and narrowband rather than natural broadband noise. There is currently no verified evidence supporting this hypothesis. None. No peer-reviewed papers claim artificial origin, no confirmed detections of signals, no orbital anomalies that demand non-natural explanations. The speculation exists primarily because Oumuamua sparked these questions, and 3I-ATLAS is the next high-profile interstellar visitor. Avi Loeb has been vocal about keeping the possibility open, which is fine in principle, but extraordinary claims require extraordinary evidence. How do you falsify this? Show that orbital residuals are smooth and consistent, with cometary outgassing. Demonstrate that light curves match natural rotation of an irregular body. Obtain spectra that clearly show ices and typical dust. Conduct radio searches that yield only noise or natural emissions. If every test comes back consistent with a comet, the artifact hypothesis dies. The burden of proof is on those claiming artificiality, not on the mainstream to disprove it. But the falsification criteria are clear. Natural explanations must fail before artificial ones are considered. Hypothesis 4. Third-party intervention. Someone, likely a state actor with advanced space capabilities, conducted a covert intercept, rendezvous, or inspection of 3I-ATLAS during the Mars window. This could be for reconnaissance, sample collection attempts, or even a nudge to alter its trajectory. This is deeply speculative and borders on science fiction with current technology, but let's entertain it. Evidence would include unscheduled maneuvers detected in the comet's orbit that don't match outgassing models, spacecraft sightings by amateur observers, leaked communications or documents, or whistleblower testimony from space agency insiders. As of now, there's no public evidence for any of this. Orbital solutions don't show sudden, unexplained changes. No credible leaks have appeared. Amateur tracking has been continuous and shows nothing anomalous. How do you falsify this? Demonstrate multi-agency orbital fits that remain consistent over time. Show that all observed position and velocity data can be explained by solar gravity and normal non-gravitational forces. No Doppler outliers, no eyewitness reports that hold up under scrutiny. If NASA, ESA and independent observers all publish data that tells a coherent, uninterrupted story of a comet on a predictable path, Hypothesis 4 collapses. The other test is technological. Does any nation currently have the capability to intercept an object travelling at tens of kilometres per second, 30 million kilometres from Earth, during a 1-week window? The answer is almost certainly no. We don't have that technology. So this hypothesis requires not just a cover-up but a secret space capability, far beyond what's publicly known. That's a tall order. Hypothesis 5. Black budget data capture. Military or intelligence assets observed 3I-ATLAS during the Mars window and collected data that's now classified or siloed. The data exists, it might even be interesting, but it's not being shared with civilian scientists or the public. Later leaks or declassification might reveal it, or it might stay hidden indefinitely. This hypothesis is harder to falsify because classified data, by definition, isn't accessible for verification. Supporting evidence would be indirect. Former insiders hinting at observations, FOIA requests that get denied with national security exemptions, or operational documents that reference the comet in classified contexts. None of that has surfaced publicly. How do you falsify it? You can't directly, but you can look for consistency. If civilian data, when fully released, is comprehensive and consistent across multiple observers, the need for a secret cache of data diminishes. If there are gaps, unexplained discrepancies, or oddities in the public record that classified data would resolve, that keeps the hypothesis alive. The practical test is whether the public scientific record eventually makes sense on its own terms. If it does, secret data might exist, but it's not necessary to explain observations. If it doesn't, questions linger. Hypothesis 6. Planetary interaction event. The close pass by Mars triggered or coincided with transient anomalies in the comet's behaviour due to space environment effects, maybe a solar wind gust, a coronal mass ejection, or interactions with Mars' weak magnetosphere caused temporary brightening, coma asymmetries, or spectral changes. These would be interesting scientifically but not indicative of anything non-natural. Supporting evidence would be contemporaneous space weather data, showing a CME or solar wind enhancement, MAVEN data showing disturbances in Mars' space environment, and ESA observations showing brightness or activity spikes during the window. This is testable and falsifiable. If Mars week datasets show no significant brightness or spectral changes, the hypothesis is wrong. If changes occurred but space weather data shows nothing unusual, the hypothesis needs refinement. If both the comet and the space environment showed coordinated changes, hypothesis 6 gains support. This is the kind of science that journals love: observable, explainable, and advancing our understanding of comet plasma interactions. For each hypothesis, I've given you predicted signatures, the kinds of data that would support or refute the claim. Now let's talk about who can test these. ESA's Mars Express and ExoMars teams will release imaging and spectroscopy. That tests hypotheses 1, 2, and 6 directly. The Minor Planet Center and JPL's orbit dynamicists will update orbital elements as more data comes in, testing hypotheses 3 and 4. Ground-based observatories, Hubble, and potentially JWST will provide post-perihelion observations, testing hypothesis 2. Amateur networks and community analysis will cross-check official releases, indirectly testing hypothesis 5. The scientific process, slow and bureaucratic as it is, will eventually answer most of these questions. The timeline matters. Perihelion occurs around October 29th to 30th, 2025. That's the point of maximum solar heating and likely peak activity for the comet. Post-conjunction observations from Earth begin in late November through December. That's when ground telescopes can see it again after it emerges from the sun's glare. Those observations will provide an independent check on everything claimed or suspected during the Mars window. If the comet's brightness, activity, and trajectory in December match predictions based on pre-Mars window data, that's powerful evidence for hypothesis 1. If there are surprises, discrepancies, or anomalies, the other hypotheses stay in play. I want to emphasize something important. Hypothesis 1, bureaucratic coincidence, is the most parsimonious. It requires the fewest assumptions and is most consistent with known facts. That doesn't make it true by default, but it's where we should start. Occam's razor suggests we don't multiply entities beyond necessity. Don't invoke conspiracy when incompetence or procedure will do. Don't invoke alien technology when a comet will do. But parsimony isn't the same as certainty. We follow the evidence wherever it leads. If the evidence eventually demands a more exotic explanation, science will go there. It did with Oumuamua, where mainstream astronomers seriously considered the artifact hypothesis before concluding natural explanations were sufficient. The same rigour will apply here. So where does that leave us? 6 hypotheses, ranked roughly by plausibility based on current evidence. H1 leads, with H6 and H2 as interesting scientific alternatives. H5 is unfalsifiable but plausible given how classified systems work. H3 and H4 are distant long shots, requiring evidence that doesn't yet exist. But all of them are testable, at least indirectly, through the data that's coming. And that's what makes this story compelling. We're not stuck in speculation forever. The cosmos doesn't keep secrets well. Light travels, trajectories persist, and instruments measure. When 3I-ATLAS reappears from behind the sun, when the shutdown ends and data flows, when scientists publish and amateurs cross-check, we'll have answers. Maybe not all of them, but enough to know which story is true. So what happens when the lights come back on? Let's talk about the post-conjunction reappearance and how we recover the truth. Part 11. The post-conjunction reappearance and data recovery. Mark your calendar, late November through December 2025. That's when 3I-ATLAS re-emerges from solar conjunction and becomes observable again from Earth. The comet will have passed perihelion around October 29th to 30th, experienced maximum solar heating, and either behaved exactly as a comet should or revealed something unexpected. By the time it's visible again, weeks will have passed, gases will have escaped, dust will have spread, and the trajectory will have been altered, however slightly, by non-gravitational forces if they exist. What we observe in December will be the consequence of everything that happened in October, a cosmic receipt for the events during the dead zone. Who's ready to observe? Ground-based telescopes, absolutely. Major observatories in both hemispheres will have the comet on their target lists if it's still bright enough. The object's magnitude, its apparent brightness, depends on how active it remains. Post-perihelion, some comets brighten steadily toward perihelion and then fade quickly as they recede from the Sun. Others remain active for weeks or months. We won't know which type 3I-ATLAS is until we watch it. Hubble Space Telescope and James Webb Space Telescope can observe if their schedules allow. These are competitive resources. Getting time on them requires proposals submitted months in advance. But target of opportunity time exists for unexpected events, and an interstellar visitor qualifies. If scientists make the case that urgent observations are needed, time can be allocated. JWST's infrared capabilities would be particularly valuable for detecting heat from the nucleus and characterizing dust composition. Then there's JUICE, the European Space Agency's Jupiter mission. According to planning documents, JUICE has a potential observing window for 3I-ATLAS in November 2025. The spacecraft is in the inner solar system, cruising toward gravity assists that will eventually fling it to Jupiter. During that cruise, instruments can be used for targets of opportunity. Thermal constraints limit when cameras and spectrometers can be powered on, but if the geometry is favourable and the comet is bright enough, JUICE could contribute unique data from a different vantage point than Earth. This would be valuable for parallax measurements and cross-validation. The priority measurements post-conjunction are clear. First, refine the orbit. More observations over a longer arc of the trajectory reduce uncertainty in the orbital elements. By December, we'll have observations spanning 6 months, from July discovery through post-perihelion. That's enough to pin down the orbit with high precision. Any deviations from a simple hyperbolic path due to non-gravitational forces will be more apparent. Second, spectroscopy. Obtain high-resolution spectra of the coma to measure gas composition. Are the volatiles water-dominated, carbon monoxide-dominated, or something unusual? Are metal lines present and at what abundances? This directly tests hypothesis 2. Third, photometry and light curves. Measure brightness changes over hours and days. A periodic light curve reveals rotation and shape. Brightness evolution over weeks reveals activity trends. If the comet brightens unexpectedly or shows irregular variations, that's noteworthy. Now let's talk about data rescue, a term I'm using to describe the community effort to archive and cross-check observations. When official data starts being released, whether from NASA post-shutdown or from ESA on their normal timeline, the community needs to mirror it immediately. Download raw files, archive them with timestamps, create redundant backups. Why? Because data can disappear, websites go down, files get moved or deleted. If you want to ensure that observations remain accessible for future verification, you can't rely solely on official servers. Amateur astronomers and citizen scientists have been doing this for years. Archive.org, distributed file systems, and community-maintained databases all play a role. For 3I-ATLAS, given the heightened interest and the shutdown complications, I'd encourage anyone with the bandwidth and technical capability to mirror official releases. Comparison spreadsheets are invaluable. Collect all published observations: date, time, observer, instrument, position, magnitude, any notes. Put them in a spreadsheet or database. Look for patterns. Do all observers see the same brightness at the same time, accounting for geometry? Are there outliers, observations that don't fit? Outliers might indicate errors, or they might indicate real anomalies. Investigating them requires contact with the observers, checking instrument calibration, and understanding observing conditions. This is painstaking work, but it's how you build confidence in the dataset. Manage expectations carefully. Science releases lag behind observations by weeks or months. Data needs to be calibrated, analysed, and written up. Peer review adds more time. During a shutdown, those delays compound. NASA might batch release data some months after collection. That's frustrating, but it's not evidence of wrongdoing. What you should watch for is consistency in the dates and quality of what's released. If NASA posts Mars Week data eventually and it looks routine, that's boring but good. If the data shows gaps, unexplained artifacts, or poor quality specifically during the key dates, that raises questions. The comparison point is other time periods. Were October observations worse than September or November observations for no apparent reason? That would be odd. What would count as a smoking gun versus normal behaviour? A smoking gun would be imaging showing structured changes inconsistent with natural outgassing. Spectroscopy revealing non-cometary molecules like industrial pollutants, or refined metals, or orbital residuals that can't be fit with any combination of gravity and outgassing. Normal behaviour is exactly what we've seen from comets before. Brightening toward perihelion, dust and gas production consistent with ices, a light curve matching irregular rotation, and an orbit fit that works with small non-gravitational terms. The baseline for comparison is rich. We've studied dozens of comets up close. We know what normal looks like. I want to encourage you to follow the Minor Planet Centre's electronic circulars, the MPECs. These are the official notices that report new observations, orbital updates and discoveries. They're published irregularly whenever there's something to report. For 3I-ATLAS, you'd search for its designation, C/2025N1, and watch for updates. When new orbital elements are published, compare them to the previous version. Did the eccentricity change? Did the non-gravitational parameters appear or get larger? Those changes tell a story. Similarly, watch ESA's image release logs, Mars Express and ExoMars TGO have public data archives. When October observations are posted, the timestamps and metadata will be there. You can check whether they actually observed during the window they said they would. One promise I'm making to you explicitly: when nickel or metal abundance claims get revisited with fresh post-perihelion spectra, we'll look at those results. If multiple independent spectrographs, from different observatories or spacecraft, all report elevated nickel, that's strong evidence. If only one source reports it and others don't, that's a calibration issue or a false positive. Science works by replication. One measurement is a hint, 3 measurements are evidence, 10 measurements are fact. Here's a reassurance that matters. NASA's shutdown is operationally constrained by law, not a science ban. The spacecraft keep flying, satellite operations continue. The only thing that stops is public communication and non-essential science planning. That means data is still being collected during the shutdown, or at least critical data. The backlog will be processed when funding returns. There's no reason to believe observations are being deliberately destroyed or withheld indefinitely unless evidence of that emerges. Treat delays as administrative friction, not malice, until proven otherwise. The post-conjunction reappearance is our second chance. The Mars window was the first, obscured by shutdown and geometry. December is the second, with clearer skies and hopefully restored funding. If we miss this window, or if it's compromised somehow, 3I-ATLAS will fade as it recedes from the Sun, and becomes unobservable except to the most powerful telescopes. The interstellar visitors don't wait for us. They pass through on their own schedules, Our job is to extract every bit of information we can while they're accessible. So watch the skies in December, watch the data releases in the months after, and watch the story evolve as facts replace speculation. But maybe, just maybe, the real secrets aren't in new data at all. Maybe they're hiding in old data we already have but haven't looked at properly. Let's talk about legacy missions and hidden clues. Part 12. Legacy missions that might hide clues. Here's a thought that should excite anyone who loves a good data detective story. What if evidence about 3I-ATLAS already exists, buried in archives we've had access to all along? Space missions collect vast amounts of data, far more than can be analysed in real time. Images are taken, sensors record, and files are stored. Years later, someone revisits the archive looking for something specific, and suddenly an object appears in the background of an image that no one noticed before. This happens. It's called a precovery or serendipitous detection, and it's how we've extended the observational arcs of comets and asteroids many times. For 3I-ATLAS, the Minor Planet Center lists the discovery date as July 1st, 2025, but that doesn't mean earlier observations don't exist. Precoveries are images or measurements taken before the official discovery, often by surveys that were looking at that patch of sky for other reasons. If 3I-ATLAS appeared in archived images from months or even years earlier, those observations could extend the baseline for orbit fitting, tightening the constraints on its trajectory. The challenge is finding them. You need to know where the comet was in the sky at earlier dates, which requires working backwards from the current orbit. Then you search image archives from observatories that were surveying those coordinates. It's tedious, but it's doable, and amateur astronomers contribute to this process regularly. Retrospective searches of Mars orbiter datasets offer another avenue. Mars spacecraft take thousands of images. Most are of the Martian surface, but some are calibration frames, dark frames, or wide-angle sky images used to check instrument performance. If any Mars orbiter happened to capture a sky frame during a time when 3I-ATLAS was in the field of view, even faintly, that's data. The odds are low because the comet is small and faint, but they're not zero. Crowdsourcing this kind of search could work. Release the pointing logs and image metadata, tell people what to look for, and let the community dig through archives. Citizen science has found exoplanets, classified galaxies, and discovered supernovae. It could find a comet. Let's use interstellar comet context to frame what counts as weird. Oumuamua, the first confirmed interstellar visitor, was bizarre. It was elongated, didn't show a visible coma, and experienced non-gravitational acceleration that couldn't be explained by normal outgassing given the lack of detected gas. Those anomalies drove the speculation about artificiality. Borisov, the second visitor, was boringly normal. It looked like a comet, behaved like a comet, and had a composition consistent with solar system comets. No one seriously suggested Borisov was artificial. 3I-ATLAS sits somewhere in between. It has a coma, which is comet-like. It shows activity, which is comet-like. But the mass and composition uncertainties leave room for questions. Using Oumuamua and Borisov as benchmarks, we can calibrate our expectations. If 3I-ATLAS ends up looking more like Borisov, the story is interesting but natural. If it looks more like Oumuamua, with unexplained features, the questions multiply. Combing Hubble and ground archives for precoveries is straightforward in principle. Hubble's archive is public and searchable. You can query by sky coordinates and date range. If Hubble imaged the region where 3I-ATLAS was located before July 2025, those images might contain the comet. Same for ground-based surveys like Pan-STARRS, the Catalina Sky Survey, or ZTF. These surveys image large swathes of sky repeatedly. Their archives go back years. Searching them systematically for the comet's predicted positions at earlier dates could yield precovery detections. Each detection adds to the orbital arc and improves the fit. The Minor Planet Center actively encourages this. They list prediscovery observations once confirmed. For 3I-ATLAS, several prediscovery observations from late June 2025 have already been identified, but earlier ones might exist. Now, here's a wildcard: IBEX and Voyager. The Interstellar Boundary Explorer, IBEX, is a NASA mission launched in 2008 that maps energetic neutral atoms from the boundary of the heliosphere. Voyager 1 and 2 are in interstellar space, measuring plasma, magnetic fields, and cosmic rays. Could they have detected anything related to 3I-ATLAS? Almost certainly not directly. The comet didn't pass near them, and they're not designed to image or track objects in the inner solar system. But if 3I-ATLAS had an unusually strong interaction with the solar wind, or if it produced an unexpected flux of particles, sensors on those missions might have seen secondary effects. This is extremely speculative. Flag this clearly, but it's the kind of cross-correlation that sometimes yields surprises. Probably not, but worth a look if you're exhausting every possibility. Amateur networks that observed 3I-ATLAS in July and August are a goldmine. Dozens of amateur astronomers worldwide contributed photometry and astrometry to the Minor Planet Center. Their measurements are independent of professional observatories and provide redundancy. If you wanted to verify that the professional data isn't being selectively reported, compare it to the amateur observations. They should align. If amateur obs show brightness variations or positions that don't match the official orbit, that's a discrepancy worth understanding. The amateur community is also motivated and attentive. They notice things. If there were anomalies visible in the data, someone likely saw them and mentioned it on forums or mailing lists. Align amateur photometry with Hubble results as a cross-check. Hubble measured the comet's brightness and coma properties in July. Amateur observers measured brightness around the same time. Do the values agree within uncertainty? They should. Accounting for differences in filters, seeing conditions and calibration methods. If they don't, why not? Investigating discrepancies is how you catch errors or uncover real physical variations. Maybe the comet was brighter when Hubble looked because it had just had an outburst. That would be interesting and explainable, provide a treasure map for the community. What time ranges should people search? From the comet's likely entry into the planetary region, months or even years before discovery up to the present. What instruments or surveys? Any that were operating and had the sensitivity to detect a faint moving object? Hubble, ground-based surveys, maybe even all-sky cameras, used for meteor observation. What sky regions? Use the comet's orbit to predict its past positions, provide coordinates and search radii. How to submit finds? The Minor Planet Center has a process for reporting observations. Guide people through it. Submitted observations get vetted, and if valid, they're incorporated into the official record. Explain the value of negative results. If you search an archive thoroughly and don't find the comet where it should have been, that's also information. It sets upper limits on brightness. It constrains activity levels. Negative results tighten the model, even if they're less exciting than discoveries. Frame this as community science to reduce the hidden data narrative. One of the frustrations during the shutdown was the sense that information was being withheld or lost. By mobilizing the community to search archives and cross-check data, you democratize the investigation. You make it harder for any single entity to control the narrative. Transparency is a forcing function. The more eyes on the data, the more robust the conclusions. When ESA and NASA do release their Mars Week observations, integrate them immediately. Compare timestamps to the planned observation windows. Check instrument modes and filters. Look at metadata for anomalies. Cross-reference with amateur observations from the same period if any exist. If everything aligns, great. If there are inconsistencies, document them and ask for explanations. This is accountability through scrutiny, not paranoia. It's how science should work. The promise here is that legacy data and community effort can fill gaps that official channels might leave. You don't have to wait passively for NASA or ESA to tell you what happened. You can dig into the data yourself, contribute observations, and participate in the analysis. The tools are available, the archives are public mostly. The knowledge is accessible if you're willing to learn, and in doing so, you're not just satisfying curiosity, you're doing science. But before we close the loop on observation, we need to address the wildest speculation of all. What if there was a signal and we missed it? Let's talk about SETI, communication, and contact hypotheses. Part 13, Signals, Communication and Contact Hypotheses. Let me be very clear about what we're entering. Highly speculative territory. The idea that 3I-ATLAS could be carrying artificial signals or acting as some kind of relay is not supported by verified evidence. There are no confirmed detections, no peer-reviewed claims, no official statements from SETI organizations. But the speculation exists, amplified by online communities and by the lingering questions from Oumuamua. So let's address it seriously and see what a genuine search for signals would entail and what it would take to convince skeptics. What would a plausible artificial signal look like? Start with the basics. It would be electromagnetic, Probably radio or optical, because those are what propagate well through space. It would likely be narrowband, meaning concentrated at a specific frequency rather than spread across a wide range. Natural astrophysical sources emit broadband noise. Pulsars, quasars, stars, they all produce signals across the spectrum. Artificial transmitters, at least the ones we build, tend to be narrowband to maximize power in a specific channel. Think of a radio station versus static. The signal would also show Doppler drift consistent with the object's motion. As 3I-ATLAS moves toward or away from Earth, its radial velocity changes, and any signal frequency would shift. That drift, if it matched the predicted motion of the comet, would be strong evidence of origin. Searching for such a signal is hard. The geometry matters. 3I-ATLAS was tens of millions of kilometers away during the Mars window. Signal strength drops with the square of distance. Even a powerful transmitter becomes faint at that range. You need a sensitive receiver. The largest radio telescopes on Earth, like the 500-meter aperture spherical telescope in China or the Very Large Array in New Mexico, have the sensitivity, but they need to be pointed at the right place at the right time. The Doppler rate complicates things. The comet's velocity relative to Earth was changing as it moved through the inner solar system. A signal's frequency would be shifting by hundreds or thousands of hertz per second, depending on the observing frequency. Searching for a drifting signal requires specialized software that can track changing frequencies over time. This is standard in SETI work, but it's computationally intensive. Radio frequency interference, or RFI, is a constant problem. Earth is noisy. Our own telecommunications, satellites, radar, and electronics produce signals that can mimic extraterrestrial sources. Distinguishing a real signal from RFI requires multiple observations, ideally from different locations. If a signal appears when you point at 3I-ATLAS and disappears when you point away, and if it reappears consistently when you point back, that's compelling. If it shows up regardless of where you point, it's RFI. There's been public chatter tying the nickel and mass claims to engineered ideas, largely driven by Avi Loeb and media coverage like articles in The Debrief or discussions on Medium. Loeb has been vocal since Oumuamua about keeping an open mind regarding artificial origins for interstellar objects. His Galileo project, funded privately, aims to search for technological signatures from anomalous objects. That's legitimate science, even if it's on the speculative edge. But media coverage often inflates these ideas. A scientist saying we should look becomes we found something in the retelling. Keep a skeptical frame. The nickel detection, if confirmed, doesn't imply engineering. Nickel is natural. The mass estimates, even if high, don't imply technology. Dense. Objects exist naturally. You'd need multiple independent lines of evidence pointing unambiguously toward artificiality before that hypothesis becomes serious. Here's a do-it-yourself angle for the motivated. Amateur radio telescopes exist. They're not as sensitive as professional ones, but they can detect strong signals. Software-defined radios, or SDRs paired with antennas and signal processing software, can record dynamic spectra, visual representations of signal frequency versus time. If you have the equipment and the interest, you could attempt observations of 3I-ATLAS yourself. What would you look for? A signal that appears at a specific frequency, drifts in a way consistent with the comet's motion and repeats. You'd want to record everything, timestamp it precisely using GPS, and share raw data with others who can attempt replication. If multiple independent observers in different locations detected the same signal, that would be extraordinarily compelling. The null hypothesis, and it's the one you should assume until proven otherwise, is that 3I-ATLAS is a comet. Comets emit broadband radiation, mostly thermal infrared from warm dust, and some ultraviolet and visible from fluorescent gases. They don't produce narrowband radio signals. If you search and find nothing, that's the expected result. It doesn't mean there's definitely no technology. It just means there's no signal detectable with the methods used. Absence of evidence is weak evidence of absence when the search is thorough, but it's not proof of absence. Post-conjunction coordinated listening windows would make sense. Organised through amateur radio and SETI communities, pick specific dates and times when the comet is at favourable geometry. Coordinate observations across multiple sites. Pull data afterward. If someone claims a detection, others can check their recordings for the same signal. This is how you build confidence. Single detections are interesting. Replicated detections are discoveries. Spell out what to look for in specifics. A signal originating from 3I-ATLAS would have a sky position matching the comet's ephemeris, its predicted location in the sky. It would have a Doppler drift rate matching the comet's radial velocity relative to Earth. You can calculate that from the orbit. The signal should be polarized or unpolarized in a way consistent with an artificial source. It should have temporal structure, maybe pulsing or modulated, rather than being a constant carrier wave, though a carrier is possible. If the signal has information encoded, that would be definitive, but decoding it is another challenge entirely. Stress testability. If anyone claims they detected a signal from 3I-ATLAS, the scientific community will demand specifics. What was the frequency? What was the bandwidth? What was the drift rate? What time did it appear? What equipment was used? Can you provide raw data files? Were there control observations pointing at blank sky? Did the signal go away when you pointed elsewhere? These questions aren't hostile, they're necessary. Extraordinary claims require extraordinary evidence, and evidence means data that others can examine and attempt to replicate. Wrap with an open-minded stance. Curiosity about whether 3I-ATLAS might be artificial is not ridiculous. The universe is vast, and the odds of other technological civilizations existing somewhere are decent, depending on your assumptions in the Drake equation. Interstellar objects could, in principle, be used for exploration by sufficiently advanced societies. It's not impossible, but improbable things require strong proof. Right now, the proof doesn't exist. The responsible position is curiosity tempered by skepticism. Search, yes. Listen, yes. But don't believe without evidence. And if evidence emerges, subject it to the most rigorous scrutiny possible before accepting it. That's how we avoid fooling ourselves. But even without beacons and alien probes, 3I-ATLAS has changed conversations. Let's talk about the broader implications for science and policy. Part 14, Implications for Interstellar Object Science and Policy. So let's assume for a moment that 3I-ATLAS is exactly what it appears to be. A comet, a frozen visitor from another star system, tumbling through our solar system on its way back to the void. Even if that's the whole truth, the story still matters, because this object, shut down silence and all, has already changed how we think about interstellar science, how we operate our spacecraft, and how we communicate during moments of uncertainty. The implications ripple outward in ways that have nothing to do with aliens or cover-ups, and everything to do with preparedness, transparency, and the fragile infrastructure we've built to watch the sky. Start with the science itself. 3I-ATLAS is the third confirmed interstellar object we've detected. The first was Oumuamua in 2017. The second was Borisov in 2019. 3 objects in 8 years. That's not a lot, but it's enough to suggest a pattern. The galaxy is not empty. There's traffic out there. Chunks of rock and ice, ejected from forming planetary systems, wandering between the stars. Current models estimate there could be thousands of interstellar objects passing through the inner solar system every year, most of them too small or too faint to detect. We're only seeing the tip of the distribution. The big ones, the bright ones. The ones that happen to pass close enough to Earth or the Sun to catch our attention. 3I-ATLAS was discovered by the Asteroid Terrestrial Impact Last Alert System Survey, ATLAS for short, on July 1st, 2025. That's a ground-based robotic telescope network designed to find near-Earth asteroids. It scans the sky every night, looking for moving objects. When it spotted 3I-ATLAS, the object was already inbound, already past Jupiter's orbit. If it had been smaller, or if it had approached from a different angle, we might have missed it entirely. That tells you something about our observational limits. We're good at spotting things that come close to Earth. We're less good at spotting things that stay far away or move quickly. Interstellar objects move fast. They're not bound by the sun's gravity, so they're on hyperbolic trajectories, swooping through the system in months rather than years. Catching them requires luck, good sky coverage, and fast follow-up observations to nail down the orbit. The fact that we caught 3I-ATLAS at all is a win for survey astronomy. It validates the investment in all-sky surveys like ATLAS, the Zwicky Transient Facility, Pan-STARRS, and eventually the Vera Rubin Observatory, which will start operations in the next few years. Rubin will be a game-changer. It will image the entire visible sky every few nights, with a camera sensitive enough to detect objects much fainter than current surveys can see. If interstellar objects are as common as models suggest, Rubin will find dozens, maybe hundreds, over its operational lifetime. That means we'll go from having a handful of case studies to having a statistical sample. we'll be able to answer questions like, what are typical interstellar object compositions? Do they resemble solar system comets and asteroids, or are there exotic types we haven't seen? How often do they come from specific directions in the galaxy, and what does that tell us about the structure of the interstellar medium or the locations of nearby star-forming regions? 3I-ATLAS, even without resolving all its mysteries, is already teaching us about survey cadence, about the importance of rapid orbital determination, and about the need for coordinated follow-up across multiple wavelengths. Hubble grabbed it in July. Ground telescopes tracked it through August and September. Mars orbiters attempted observations in early October. That's a multi-platform campaign spanning space-based and planetary assets. It's a proof of concept. It shows that when an interstellar object appears, we can mobilize. But it also exposes gaps. During the Mars window, Earth-based observers were handicapped by the comet's low solar elongation. It was too close to the Sun in the sky. Mars orbiters had the geometry, but they're not designed primarily for comet observations. They're planetary science missions. Imaging a distant comet is a bonus, a target of opportunity, not a core objective. That brings us to operations and mission design. If we expect more interstellar objects in the future, and we do, then it makes sense to think about building quick response capabilities into our missions. Mars orbiters could carry modest wide-field images or spectrometers optimized for transient events. Earth-orbiting telescopes could reserve discretionary time for sudden interstellar arrivals. There's precedent for this. Hubble and the James Webb Space Telescope both have director's discretionary time, which allows rapid scheduling for unexpected targets. But the process still takes days to weeks, and by the time you get approved, the object might have moved out of optimal viewing geometry. What we need is faster. Automated triggers, pre-approved observation templates. When an interstellar object is detected, the system should be able to say, "Koko wa konoyuna Zhongquang desu." Here's the orbit, here are the available instruments. Execute this observation plan within 24 hours. No committee meetings, no proposal writing, just go. The Mars window for 3I-ATLAS illustrated the value of having eyes in multiple locations. When Earth couldn't see it well, Mars could. That's a spatial advantage. In the future, we might have assets further out. JUICE, the Jupiter Icy Moons Explorer, is en route to Jupiter and will arrive in 2031. Psyche is headed to the asteroid belt. If an interstellar object passes through the outer solar system, those missions could provide views that Earth-based telescopes can't match. The same logic applies to the interstellar probes we've discussed in science fiction. If we ever send a probe to another star, it could serve as an early warning system for interstellar objects heading our way. It's a long shot, but it's worth thinking about. Now let's talk about transparency and communication. The shutdown, whatever your interpretation of it, exposed a weakness. NASA's public-facing infrastructure went dark right when a scientifically interesting event was happening. The agency's own continuity plan says it outright. During a lapse in appropriations, the public won't have access to NASA's website or social media or television broadcasts. That's policy, not conspiracy. But the optics are bad. It creates an information vacuum, and vacuums get filled with speculation. People assume silence means something's being hidden, even when the silence is just bureaucratic procedure. The European Space Agency, by contrast, continued updating its plans and posting statements about the Mars Express and ExoMars Trace Gas Orbiter observation campaign. That asymmetry, NASA quiet and ESA vocal, made the shutdown look more suspicious than it probably was. It handed ammunition to conspiracy theorists who were already primed by Oumuamua to expect secrecy around interstellar objects. The lesson here is that transparency during anomalies or shutdowns is not optional. It's necessary to maintain public trust. Even if the message is just, we're observing, data is being collected, results will be shared when we're back online. That's better than silence. Silence breeds doubt. Future shutdowns, and there will be future shutdowns, should have contingency plans for public communication. A skeleton crew maintaining a basic website update. A social media account posting minimal status reports. Something. Anything. The cost is trivial compared to the reputational damage of appearing to hide information. And if there's ever a real emergency, a genuine anomaly that requires immediate public communication, the current shutdown policy could delay that communication at exactly the wrong time. Space agencies need to think about this. What happens if an interstellar object turns out to be genuinely unusual? What if we detect something that looks artificial, or something that poses a hazard? Who decides when to speak? And what's the chain of communication if normal channels are offline? These are not hypothetical questions anymore. 3I-ATLAS, whether it's normal or weird, has put them on the table. Data policy is another pressure point. Right now, most planetary mission data is released in batches, often months or years after it's collected. That's standard practice. Science teams get proprietary access for a period, then the data goes into public archives. It works fine for routine science, but it's a poor fit for transient events. Interstellar objects don't wait. By the time data is formally released, the object might be gone, too faint to follow up. A better model would be rapid raw data dumps for high-priority targets. Post the images and spectra within days, even if they're uncalibrated, even if they're messy. Let the community dig in. If something's anomalous, crowdsourcing can catch it faster than a small mission team working alone. If it's normal, fine, everyone moves on. The risk of releasing early is low. The risk of waiting is that you miss the chance to coordinate follow-up observations while the object is still observable. International collaboration came through during the Mars window, at least on the European side, and that's encouraging. If interstellar objects become more common, we'll need a standing international framework for coordinating observations. Think of it like the International Astronomical Union system for comet and asteroid designations, but expanded. A network of space agencies, ground observatories, and amateur astronomers, all feeding data into a shared platform. When an interstellar object is detected, the network activates. Observation plans are shared. Data is pooled. Results are cross-checked. No single agency owns the object. No single country claims discovery. It's a global scientific target. That kind of collaboration requires formal agreements, memoranda of understanding, pre-negotiated data-sharing terms. Right now it's ad hoc. ESA and NASA cooperate on some things, compete on others. Data sharing is often bilateral and slow. If we want to be ready for the next 3I-ATLAS, or for something even weirder, we need better infrastructure. And we need it before the object shows up, not after. Let me touch briefly on resources, because it keeps coming up in the speculative corners of this story. If a future interstellar object turns out to be metal-rich, genuinely rich, like a differentiated planetesimal core fragment made of iron and nickel, what do we do? The economics of asteroid mining are already being debated for solar system objects. Interstellar objects add a twist. They're moving fast. You'd have only a short window to intercept and sample them. The delta V requirements are high. It's not practical with current propulsion. But if you could do it, the scientific return would be enormous. A sample of material from another star system delivered to Earth orbit would be worth more than any meteorite. The legal side is murky. Space law, specifically the Outer Space Treaty, says no nation can claim sovereignty over celestial bodies. But it doesn't say you can't extract and use resources. There's ambiguity there, and interstellar objects sit in the most ambiguous zone of all. They're not part of anyone's solar system, they're just passing through. If you can catch one, can you keep it? Probably. But the ethics are another question. Instrumenting future missions for interstellar object science doesn't require exotic technology. You'd want wide-field cameras for detecting and tracking, spectrometers for composition, photometers for brightness and variability, maybe a radar if you're close enough. These are off-the-shelf tools. The challenge is scheduling and quick reaction, not capability. Mars orbiters could do it tomorrow if they had the operational flexibility. Earth orbiters already do it when they have discretionary time. What's missing is the cultural shift, the recognition that interstellar objects are common enough to justify designing missions with them in mind from the start. Public literacy matters too. One reason the metal core speculation and the engineered artifact theories gain traction is that the general public doesn't have good intuition for how uncertain comet measurements are. When you see a number like nucleus diameter 0.32 to 5.6 kilometers, most people don't realize that's an order of magnitude of uncertainty. They pick the number they like and run with it. Science communicators need to do better at explaining error bars, at making it clear that "we don't know yet" is a legitimate scientific answer. The alternative is that every ambiguity gets filled in by the most dramatic interpretation, and that's how you end up with alien mothership theories. So here's where we are. 3I-ATLAS has demonstrated that interstellar object science is real, that it's happening now, and that we're not quite ready for it. The tools exist. The interest exists. What's missing is coordination, speed, and transparency. The shutdown was a stress test, and we didn't pass with flying colours. but we can learn from it. We can build better systems for the next time. Because there will be a next time. The galaxy is full of these things, and our surveys are getting better every year. And if one of them turns out to be more than a comet, if one of them really is something we've never seen before, we'll need all of that infrastructure, all of that transparency, all of that international collaboration to figure out what it means. The question isn't whether we'll find something extraordinary, the question is whether we'll be ready when we do. Which brings us to the end, or at least to the end of this particular mystery, because the story of 3I-ATLAS isn't over, it's just paused, waiting for the lights to come back on. Part 15. Synthesis, Open Ends and Actionable Promises. So let's come full circle. Midnight, October 1st, 2025. The United States government shuts down. Hours later, we enter the Mars observation window for the interstellar visitor 3I-ATLAS. Was it coincidence? Or was it a cover? You came here for an answer. I'm going to give you one, but it's not going to be simple, and it's not going to satisfy everyone. The truth, when you dig through all the data and all the noise, is that both things can be true at once. The shutdown was real, the silence was procedural, and yet the timing created exactly the conditions that would allow something unusual to be downplayed or delayed, if there was something unusual to downplay. That ambiguity is the story. Let's lay out the hard facts first. NASA was closed to the public. The agency's continuity of operations plan, the one they filed and published, says it plainly. During a lapse in appropriations, most activities cease. Public communications stop. The website goes dark. NASA TV goes offline. Social media pauses. The only accepted operations are those necessary to protect life and property. That includes the International Space Station, satellite ground control for anything that could crash or malfunction, and critical Artemis program safety work. Mars orbiters fall into that category. Mars Reconnaissance Orbiter, MAVEN, they're expensive hardware flying in a harsh environment. You don't furlough the people keeping them from dying. So flight operations continued. Commands were sent. Data was collected. What didn't continue was the public-facing layer, the press releases, the image of the day postings, the tweets. That's the gap everyone noticed. The European Space Agency, meanwhile, announced openly that Mars Express and the ExoMars Trace Gas Orbiter would attempt observations of 3I-ATLAS during October 1st through 7th, with closest approach around October 3rd at roughly 30 million kilometres. ESA posted statements. Mission scientists gave interviews to Space.com and other outlets. There was no blackout on the European side. That transparency makes NASA's silence stand out more sharply. It also makes certain conspiracy theories harder to sustain, because if something world-changing had been observed, ESA would have been seeing it too, and ESA wasn't being quiet. Perihelion for 3I-ATLAS happened around October the 29th or 30th, 2025. That's the point where the comet was closest to the Sun, about 1.36 astronomical units out, inside Earth's orbit, but not dramatically so. After perihelion, the comet swung outward and passed behind the Sun as seen from Earth, entering solar conjunction. During conjunction, you can't observe it from Earth. The Sun's glare blocks the view. That blackout period extends through most of November. Late November or December, the comet emerges on the other side of the Sun, far enough away that ground-based telescopes can pick it up again. That's the reappearance window. That's when we get fresh data. So as of the time this script is being written, early October, we're in a strange in-between zone. The Mars observations happened, or they were attempted, depending on which agency you're talking about, and what you consider a successful observation. The data from those observations hasn't been released yet, not in detail. That's expected. Data releases from Mars missions often lag by weeks or months. The shutdown delays things further, because even though the spacecraft kept operating, the people who process and publish the data were furloughed. They're back now, presumably, but the backlog exists. The perihelion passage is happening right now, the conjunction blackout is starting, and the big reobservation campaign is still in the future. That means everything we've talked about, all the speculation, all the theories, they're hanging in a state of unresolved tension, which is exactly where a good mystery should be at this point in the story. But it also means we have a playbook for what comes next. We have checkpoints. We have things we can watch for. If you want to know what really happened, if you want to separate the coincidence from the cover, here's what you do. First, watch the Minor Planet Center. The MPC is the official clearinghouse for solar system object observations. Every time someone makes a positional measurement of a comet or asteroid, they report it to the MPC, and the MPC publishes it in a Minor Planet Electronic Circular, an MPEC. These circulars are public. You can read them yourself. For 3I-ATLAS, the MPC has been publishing MPECs since the discovery in July. Each circular includes observations from different telescopes and observatories, and each observation refines the orbit. If there were anomalies during the Mars window, big anomalies, gravitational perturbations or non-gravitational accelerations that didn't fit the model, they'd show up in the orbital solutions published in November and December. The MPC doesn't editorialize, they just publish the numbers. If the numbers from multiple independent observatories all agree, that's a strong sign the orbit is being modelled correctly. If the numbers diverge, or if there are unexplained residuals, that's a red flag. Second, watch the European Space Agency's Mars mission pages. ESA is usually good about posting image releases and instrument status updates. If Mars Express or the Trace Gas Orbiter captured anything interesting, it'll show up eventually. Maybe not immediately, maybe not, with full analysis, but the raw images or spectra will surface. When they do, compare them to what was expected. Compare the timestamps to the planned observation windows. Check whether the data matches the predicted brightness and motion of the comet. If everything lines up, that's evidence in favour of the boring explanation. If something doesn't line up, that's where you start asking harder questions. Third, follow NASA's post-shutdown data drops. When the shutdown ends and funding resumes, NASA will start posting backlog data. Look for updates on the 3I-ATLAS mission page on nasascience.gov. Look for Hubble or JWST observation logs. Look for any mention of Mars Reconnaissance Orbiter or MAVEN attempting observations. If those observations happened, the metadata will exist. The timestamps, the instrument modes, the target coordinates. Even if the full analysis isn't ready, the log should be. If the logs are missing, or if there are gaps during the Mars window that don't align with the expected shutdown procedures, that's unusual. It's not proof of anything, but it's unusual. Fourth, watch for scientific papers. The team that imaged 3I-ATLAS with Hubble in July published a preprint on ARC. That's where you go for early results. irciv.org. Search for 3I-ATLAS or C/2025N1. If new papers appear with Mars window data, read them. Check the author lists, check the acknowledgements, see who funded the work, see what instruments were used. Papers go through peer review, and peer reviewers check the data. If something weird is in the data, it'll either get caught and questioned, or it'll get published and debated publicly. That's how science works. It's messy, it's slow, but it's transparent in the end. Fifth, listen for the reappearance. When 3I-ATLAS comes out of solar conjunction in late November or early December, amateur astronomers and professional observatories will start tracking it again. They'll post images. They'll measure brightness. They'll take spectra if they have the equipment. You can follow this in real time on forums like Cloudy Nights, or on Twitter accounts run by comet observers. If the comet looks normal, if its brightness curve follows the predictions, if the coma is behaving like a comet coma should, that's strong evidence it's just a comet. If there's something off, if it's brighter or dimmer than expected, if the spectrum shows unusual lines, people will notice, and they'll talk about it loudly. Sixth, coordinate your own observations if you're able. I mentioned in the previous section that amateur radio telescopes could attempt to search for artificial signals. I'm not optimistic about success, but the attempt is worth making. If you have access to a software-defined radio and a decent antenna, you can record a dynamic spectrum aimed at 3I-ATLAS during the reappearance window. Use GPS timestamping so your data is comparable to others. Use open source, software like GNU Radio or SDR Sharp. Record in a format that others can open and analyze. Share your raw data. If 5 people in 5 different countries all record the same signal at the same frequency, with the same Doppler drift matching the comet's motion, that would be extraordinary. It would be Nobel Prize territory. It hasn't happened. It almost certainly won't happen. But the fact that you can try, the fact that the tools exist and the information is public, that's important. It means the search isn't locked behind classified walls. It's accessible. It's democratic. So now rank the hypotheses. Hypothesis 1, bureaucratic coincidence. The shutdown was timing, nothing more. NASA's public communications paused because of funding rules. Data was collected normally. Results will be released on a standard timeline. This is the most plausible explanation. It requires the fewest assumptions. It fits the known facts. It doesn't require any conspiracy or cover-up. It's boring, but boring is often correct. Falsification. If ESA or other international partners publish data that contradicts the predictions, or if orbital solutions show unexplained perturbations that NASA somehow failed to mention, then the coincidence hypothesis weakens. Hypothesis 6. Planetary interaction event. Solar wind or Martian gravitational effects cause transient changes in the comet's activity or trajectory during the Mars window. This is plausible for a comet, because comets are volatile. They respond to their environment. A gust of solar wind could temporarily brighten the coma. A gravitational nudge from Mars, small as it would be at 30 million kilometers, could show up as a minor perturbation in the orbit. Falsification. If Mars-weak datasets show no brightness spikes, no spectral changes, and no orbital residuals, then this hypothesis loses support. Hypothesis 2. Massive metallic core. The comet has an unusually high mass and density, possibly a metal-rich interior, consistent with a planetesimal core fragment. This is speculative. It's based on unconfirmed nickel emission reports and on mass estimates that sit at the high end of the allowed range from Hubble imaging. The idea isn't crazy. Differentiated bodies do exist, and fragments of their cores could be ejected into interstellar space. But right now, the evidence is weak. Falsification. If better size and albedo measurements constrain the nucleus to the small, low-mass end of the range, and if spectra show normal cometary volatiles without exotic metal abundances, then the metal core hypothesis collapses. Hypothesis 5. Black budget data capture. The data from the Mars window exists but is being withheld or classified by military or intelligence agencies. This is hard to evaluate because classified information, by definition, isn't public. But there's no positive evidence for it. No leaks, no whistleblower claims, no documents. The hypothesis relies entirely on absence, falsification. If data is released normally after the shutdown, with timestamps and content consistent with unclassified observations, then there's no reason to assume hidden data. If data never appears, that's consistent with the hypothesis, but it's also consistent with the observations never happening or failing for technical reasons. Hypothesis 4. Third-party intervention. A covert actor, either a space agency or a private entity, performed a close flyby or sample collection during the Mars window. This is the least supported hypothesis. It requires technology that may or may not exist, secrecy across multiple agencies and countries, and motivations that are unclear. Falsification. Consistent multi-agency orbital fits with no anomalies and no Doppler outliers in independent observations would rule out any significant intervention. Hypothesis 3. Engineered or technological artifact. 3I-ATLAS is not a natural object, but a probe or derelict spacecraft from another civilization. This is the most extraordinary hypothesis. It has the highest burden of proof, and right now, the proof doesn't exist. No verified signals, no verified anomalies, no verified structural features inconsistent with a comet. The hypothesis exists because of Oumuamua, because Avi Loeb has kept it in the public conversation, and because people want it to be true. Falsification. If the comet's light curve, spectrum, and trajectory all match natural cometary behaviour, and if no signals are detected despite competent searches, then the artifact hypothesis is unsupported. It doesn't mean it's impossible, it just means it's not justified by the data. That's the ranking. The mundane explanations come first, the exotic ones come last. That's how you should approach any mystery. Start with the simple, only move to the complex when the simple fails to explain the observations. So what's the promise? Here's what I'm committing to, and what I'm asking you to commit to. When the data comes out, when the papers are published, when the images are posted, we revisit this. We check the receipts. Did NASA post HiRISE or Mars Reconnaissance Orbiter thumbnails from the Mars window? If yes, what do they show? Are the timestamps consistent with the planned observations? Do the images show anything anomalous, or do they show a fuzzy dot behaving like a comet? Did ESA release HRSC or CASS's data? If yes, does it match the predictions? Are there brightness spikes, spectral surprises, anything off-model? Did the Minor Planet Center update the orbital solution with post-perihelion data? If yes, did the residuals shrink or grow? Are there non-gravitational parameters in the fit? And if so, are they consistent with outgassing? We go through this checklist item by item. We compare what was promised to what was delivered. we note discrepancies, we note confirmations, and we adjust our credence accordingly. If everything checks out, then the mystery was mostly in our heads, a product of bad timing and poor communication. If things don't check out, if there are gaps or contradictions or data that doesn't fit, then the mystery is real, and we escalate. We ask harder questions. We demand better answers. You don't need a PhD to do this. You don't need access to classified briefings. You need patience, you need a browser, you need the ability to compare a timestamp to a calendar and to check whether a published number matches a prediction. That's it. The tools of verification are public. Use them. And here's the final thought, the one that should stick with you after this whole journey. If 3I-ATLAS were engineered, if it were a probe or a relay, or a piece of ancient alien infrastructure, it wouldn't hide quietly in the pixels of a single dataset. It would leave a trail across telescopes, across wavelengths, across months of observations. It would show up in the astrometry, in the photometry, in the spectroscopy. It would show up in ways that couldn't be explained by ice and dust. That trail is what we're following. Not rumours, not speculation. The trail of data. And the trail is public. Or it will be, once the conjunction ends and the observations resume. So when the lights come back on at NASA, when the website updates resume and the press releases start flowing again, we'll see if the story matches the logs. We'll see if the silence was policy or if it was something more. We'll see if 3I-ATLAS was a comet caught in bad timing or if it was the opening act of something stranger. Until then, keep watching the sky, keep checking the sources, and keep asking the questions that don't have easy answers. Because the universe doesn't owe us easy answers. It owes us nothing. But if we're persistent, if we're careful, if we're honest about what we know and what we don't, we might just find the truth anyway. The shutdown is over. The comet is rounding the sun, the data is coming, and we'll be here, waiting, ready to piece it together when it arrives. This is the part where I'd normally say, see you next time, but the truth is, the next time is already scheduled. Late November, early December, when 3I-ATLAS emerges from behind the sun and the telescopes lock on again. That's when we reconvene. That's when the answers start coming in. And if the answers are boring, if it's just a comet, that's okay. Because the process, the investigation, the communal effort to figure it out, that's never boring. That's science. That's how we separate the signal from the noise. That's how we keep ourselves honest. But if the answers aren't boring, if there's even one piece of data that doesn't fit, one measurement that defies the models, one signal that can't be explained away, then this story is just beginning. And you'll want to be here for what comes next. So mark your calendars, follow the sources, download the data when it drops, compare notes with others who are doing the same, build the case piece by piece, and when we have enough pieces, to see the picture, we'll know. We'll know if October 1st, 2025 was the night the government went dark by accident or by design. We'll know if 3I-ATLAS was a comet or a calling card. Until then, the mystery hangs in the space between what we saw and what we didn't, between what was said and what was silent, between coincidence and cover, and that space, that uncertainty, that's where all the best stories live. The lights are coming back on, let's see what they illuminate.